Okay. I teach every class using a package called Screencast-O-Matic. That's what I just opened, okay? And you can't see it, but see, we're recording right now. It's sort of hard to see. I don't know how these lights do. Yeah. Are y'all got enough light that you can see to write, but you can see the board better, can't you? Okay. Did I call roll when you were in here? Okay, what's your name, please? Okay, I've lost the roll. Let me get it. Say that again. Oh, Terry Wright. I was wondering where you were. Okay, there you go. All right. So I teach using Screencast-O-Matic. That means all of the first day's class is out there. Where is out there? It's in YouTube land somewhere, okay? Now, I don't have it set up so you can access it easily. I'm going to try to do that tomorrow and maybe over the weekend. What I'll do is I'll get a link. I'll set up a YouTube playlist for this class and then get the link to that playlist and put it on Blackboard. Okay, now I hope all of you are familiar enough with Blackboard. You know, when you pull up Blackboard, in the upper left quadrant here, there's a bunch of tabs. About the second or third one down is one that says Content. Content is where I'll put the syllabus. It's not there yet, but I'll put that. I'll put the research paper instructions, okay? I will put all the PowerPoints that we'll be using. And I will put my locator card when I'm in class, when I'm not in class, when I've got office hours, when I don't. It will be posted on my door too, but you'll be able to see it from Blackboard. And I'll put a bunch of several files or links and things that I've received, either I found myself or students have given me, that show really neat stuff in astronomy or other areas. And if you find stuff that's really neat, I'll put that out there too. Just send it to me and we'll talk about it. If it looks like it's legitimate, I'll put it out there. Okay? So those will be there. And then somewhere near the bottom, I'll have one that says YouTube videos or something like that. When you click on that, you'll be able to get it. So what we did last time, we went over the syllabus. It wasn't up to date yet, but all the vital stuff was there. Just days and times were wrong, but all the basic information was there. So it's out there. I went over the research paper. I have a few corrections to make there, but I explained those. It's out there on the YouTube video. And we went over safety, okay? Now, a few safety items changed from this room. We were in the other classroom. If there were a fire or weather situation, okay? Right now, the closest exit is right here. So fire, you would go out here and go down and out of the building. If it was weather, you go down and into the interior. But again, just like I said before, stay away from windows with exterior. Now, you and I would have to make our way around, and we would do that and find a place safe there. And then after you're settled, then I would come back and catch a roll with everybody else. Okay, now, the third one that I don't even like to think about, and I especially don't like to think about it in this room, is active shooter. Because I don't have any keys to this and there's no buttons to push, okay? So if there were an active shooter, and we need to sort of be able to think through these things. Nothing here either. Okay, what I would suggest that we do is we're going to close these doors, and I'm going to start pushing every table that I can push against these two doors, okay? And then we'll get under the tables, okay? Or something like that. That's the best thing. No way to block this out. We may, put paper over this, turn off the lights, someone call 911, all that kind of stuff. But that's what we would have to do, because I cannot lock this door, either one of these doors. My other classroom, I could, not this one. I was thinking about my office. I could lock my office, but it's got glass, and someone could break the glass and reach in and unlock it, so that wouldn't be safe. So what we would do, I would just immediately, if y'all hear gunfire, here's what we do. We just start putting tables in front of both doors. Move as many tables. Computers can go on the floor. I don't care. Move as much as you can in front of the doors, and make it just as difficult as possible. And if you don't want to get under tables, the better place would be against the wall, so you wouldn't be you'd be out of sight. Okay, but that's the best I can come up with now. Sorry about that. I will check and see if there's some better solutions. But for now, which hopefully it's not going to happen. It's only happened once in the whole history of community colleges that I know of, and nowhere close to here. So hopefully it won't happen. But I like to always plan, even when it's bad stuff to plan for. Okay. Whew. Didn't want to go through that again, but we had to. All right. So I was talking about, we talked about it. So all those safety issues are there. Then we started chapter 1. I mean, not chapter 1. We started the first chapter we're doing, and that's chapter 14. Now, if you have a big, thick book, that's about the middle of the book, about right there. If you have the thin book, it's the very first chapter in there. As I said before, we're studying the universe. We should do that in a day or two. No, I'm just kidding. Okay. So we got started on it. We went through star formation. We went through a lot of that. We're right now toward the end, getting close to the end of chapter 14. And for some reason I had marked something here. I think what the deal was, we're going to start on the galaxies today. But I put my notes the page before because I did skip sort of an important thing, and for some reason thought we already had this up, but it hadn't come yet. All right. If I seem disjointed, I am. All these changes. Goodness, is this room hot to y'all? Okay, I am burning up, but maybe it's because I've been running all over the building trying to find us a room to be in. All right, here we go. We are awfully close to the end of this chapter, okay? We're starting today in larger scale structures. We are almost there. Okay, but before we go there, let's go back a page, and if you got depending on which text you have, it's somewhere near 363. Now, the little books have page numbers at the top and at the bottom. I'm talking about the bottom page numbers, around 363. But some are different editions, so it's somewhere closer there. It says Science and Society, Light Pollution. It's actually what we talked about last time, but there's a little blurb on it here, and I wanted you to be able to read this and think about the questions that are asked there, okay? Because we talked about it some. My story of Max and Bill running through the soybean field, listen to the YouTube video and you'll catch that story. But anyway, there's some more detailed things there. Now, on the next page, 364, whatever the page close to that is, observing with new technology. Okay? They have a nice little blurb here about, and I'm not sure all the books have this, but this edition does, some of the newer technology that are out there and some of the ways we study them. Now, this goes into a lot of detail, kind of based on the physics chapters that we haven't done, so I don't want to spend a lot of time on it, but just to let you know, there's a lot more than one way to look at something, okay? For instance, you look and see a star out there. Twinkle, twinkle, little star. You see it, okay? Using the Chandra telescope, it studies the X-rays, not the light, the X-rays, the high energy radiation coming out of there. And, you know, you can read what's said here. So does the XMM Newton studies X-ray. It's an X-ray telescope. It was launched or built, both of those in 1999. Now, why two in the same year, I'm not sure. Then the Spitzer Space Telescope in 2003 is an infrared telescope. What is that looking at? Infrared, heat radiation, okay? Not light, not X-rays, but long-length radiation, low energy heat, infrared radiation. If you think about your your X-ray, your electromagnetic spectrum, the highest energy is the shortest wavelength. That's your gamma rays, your X-rays, some of the others, and then you get ultraviolets. Those are the ones that give you skin cancers and wrinkles and tan your skin and all that kind of stuff. Then you get the visible spectrum, violet, indigo, blue, green, yellow, orange, red, and then below red, longer wavelengths, lower energy, lower frequency, you get the infrared. And then you get radio waves and microwaves and stuff all scattered in through it there. So that studies infrared radiation. The Fermi, by the way, that's a pretty famous physics name too, could be a paper topic if you're interested. Gamma ray telescope measures gamma radiation. Very high energy, very short wavelength coming out of the structures, even higher energy than the X-rays. The Arecibo Observatory is a single dish radio telescope that measures radio waves coming out. Low energy, long wavelength radio waves. Okay? And then the Very Large Array, VLA, a 27-dish radio telescope, again measuring long wavelength, low energy, low frequency radiation. So just to get an idea, there's a lot more than one way to look at stars and celestial objects. Okay, that said, let's move on now to large-scale structure. First, any questions from anything that we've covered so far? Syllabus, research paper, my schedule, what we covered in the first part of the chapter. Maybe a good place to time out here and also mention this. We are going to finish chapter 14 today, okay? We'll go on and get started in chapter 15. But the last 2 hours, the lab time, we will do the lab for 14, okay? Then, on Wednesday of next week, y'all do know the good news, bad news situation, don't you? Yeah. The good news is next Monday's a holiday. But the bad news is we won't be meeting as a class. Sorry about that. Get over it, okay? So, we will meet again next Wednesday. No, wait, today's Thursday. I'm sorry, that's for Monday, Wednesday classes. I'm totally messed up. Tuesday we'll be meeting. Tuesday we'll continue chapter 15, have a fair chance of finishing 15. If we do, we'll have a lab on chapter 15, but it'll start earlier because the last 30 minutes of the class on Tuesday will be your test on chapter 14. I always put the test at the end. That way, if you finish early, you can leave. You don't have to sit around waiting for everybody else to finish the test so we can go back to class. I put it at the end so you can leave. If we don't have a test, then the lab is going to be the last thing. So if you finish the lab, you can leave when it's through, okay? And that's why the lecture will always be the first, approximately 2.5 hours, except on test days it'll be 2 hours, then 2 hours of lab, and then 30 minutes of test. Without a test, 2.5 hours of class and 2 hours of lab. All right, so getting back to this. I've already hinted at some of this last time, but some of you weren't here, so let's go over it again. We talked about things up to stars. Okay, now stars are pretty big, massive. Okay, we'll talk about something like this next chapter, but if you took everything in the solar system, all the planets, all the moons, all the asteroids, all the comets, everything in our solar system, and added them together, the sun is still many times more massive than that, okay? So the stars are huge, massive, and ours is an average sun. Average size, average heat, average everything, okay? But there's bigger things than stars. Larger scale structures. Now, I mentioned this last time. What is not unique about our sun, but one of the unusual things about our sun is a unitary star. Most stars are not unitary. And in fact, I'm not sure that we could have life on this planet like we're used to if we had a binary star. One of those is going to be hotter or colder than the other, or when you get in one position, I don't know how we would do as a habitable planet around a binary star. I can't fathom it. But what a binary system is two gravitationally bound stars that basically revolve around each other. Most stars in the universe are binary pairs. Ours is one of the relatively few that are not. There's plenty of them out there that are not, but most of them are binary. Now, I think since this book has been done, or certainly since the slide was done, they found out there are also tertiary, quadrary, there are up to 6 stars that sort of move around each other, okay? Rather strange, but true, but very rare. Most are binary, okay? Now, some of those binary systems, and we saw this on the Hertzsprung-Russell diagram, we saw, I believe Sirius is one that has a main sequence star, but the other star is on its way out, okay? It's already past its prime. So quite often the pairs are like that. So sometimes the one star will be small, you know, and dying, and the other one will be big and glowing as normal. So next after that we have star clusters, okay? These are either tens, like 10, 20, 30, up to hundreds of, tens of thousands up to hundreds of thousands or more gravitationally bound stars, okay? That sounds like a lot. That's really a piddling amount, okay? Tens of thousands up to hundreds of thousands. The stars that sort of cluster together and they kind of move around each other. They may have planets around them and stuff like this. That the other stars aren't close enough to really bother them. They'll be pretty bright, but you know, other than that, they would be. But whether they're habitable or not, we don't know. But these are bound together gravitationally. They often share a common origin. Perhaps, remember those huge stars, the most massive stars, they're the hottest stars. Those have the supernovas when they die, and they die fairly young, only millions of years, okay? That's young for stars. Our star, by the way, expected lifetime about 10 billion years. The very smallest stars, the coolest stars, they will live trillions of years, okay? So what if one of these great big massive stars that's very hot died young after a few million years and had a supernova and blew gases all over the place, and then those gases formed again to form these smaller stars? They all were one time connected to each other, so gravitationally they're still connected. Often share the common origin. Okay? Beyond the star clusters, I hate moving over here because my microphone's in my computer, we have the galaxies. Okay? What galaxy do we live in? The Milky Way, yes. Does anyone know our closest neighbor galaxy? Andromeda, exactly. They strained it. Never mind, that's a different issue. Okay, so the galaxies are, and get this, the basic unit of the universe. You mean we're not the basic unit of the universe? Nowhere close. Stars aren't the basic unit of the universe? Nowhere close. Galaxies are the basic units of the universe, and they are huge. Basically, putting us in perspective, we are smaller than a bit of dust, okay? Almost insignificant compared to the universe. Can you get your name, please? Huh? Bianca, got it. I know you're in here. There you are. Good deal. Oh, the other thing I meant to ask when I called roll, I told you I was going to, I forgot. I forgot to mark if you stayed for lab last time. We really didn't have a lab, but the last 2 hours, did any of you have to leave before the last 2 hours were over? I didn't think you did, but I couldn't tell for sure. I marked you all present, so freebie if you weren't, okay? Okay. So, you have basic unit universes and galaxies galaxies are made up of billions upon billions, not tens to hundreds of thousands. I said that was a drop in the bucket. Billions and billions of gravitationally bound stars, okay? We'll talk a little bit more about that later. Enormous, okay? Absolutely incredible. But we get larger still. We have, just like we have star clusters, we have galaxy clusters. Now, I'm guessing we're in a cluster with Andromeda, but I haven't seen the whole cluster, so I don't know. And then you have superclusters of galaxies, okay? And these are made up of billions and billions of galaxies, each of them made up of billions and billions of stars, and a few of those have little rocks circling around them that we call planets. We are minuscule compared to the universe. It's kind of humbling, isn't it? Okay? Amazing. And as we said, we live in the Milky Way. Why is it called the Milky Way? Because I think those early guys out there lying down looking at the stars, making up stories about them overnight, there was this streak that goes across the sky. You can tell there's stars in them, but they're just so many and so far away, it just looked like someone spilt milk in the celestial sphere, okay? And a stream of milk went across, and that's what it looked like. The Milky Way is visible as a diffuse, meaning not really individual stars are able to pick out, but diffuse band on a dark night, okay? We're pretty close to a full moon now, and in the light pollution around Birmingham and Bessemer, you probably aren't going to see the Milky Way. But get out in the country somewhere, and you probably still have a hard time seeing it well now because the moon's so bright. But when the moon gets pretty thin, we call it a crescent moon, or even a new moon, or the moon's not even risen, come up yet, or is already set, on a clear night, very dark night, you'll see out in the country that spilled milk across the sky. Just a diffuse band of light, but not very bright light, okay? Billions of stars, some bound in galactic clusters, is what you're looking at, okay? But mostly you're looking at stars in star clusters. I think they really meant this to be star clusters, is what you're looking at. Because really you're looking at our galaxy, so that wouldn't be galactic structures. So what's the structure of our galaxy, which a lot of galaxies are, though there are some other kinds? First you have what they call a galactic nucleus. Now here is actually a picture, and my guess this is probably out in the desert somewhere with no houses, no street lights, nothing around, dark night, no moon. They took this picture with a telescope maybe, but they took it with something, at least the camera. And this is the Milky Way. You see, you can't identify, there's stars out there, but you can't pick out individual stars. That's why they say a diffuse band light that you see on the dark night. What you're doing, you're looking into the Milky Way. We're in the Milky Way. You're looking one direction into it, okay? We'll talk about these out here. They're not quite outliers, but something like that. They're not outright liars either. Okay. So you have a galactic nucleus. Now, I can't look at that and tell you what or where that is, but if I was pressed, I would say that's probably the galactic nucleus in that direction. Okay? We'll see a better illustration of that coming up here, I think. Here we have it. The galactic nucleus is here. Now, this is two views. If you were on top of the Milky Way looking down at it, this is what you see. The galactic nucleus there and spirals coming out from around, circling like this. We live right there, okay? Again, average to below average. We're nowhere close to that galactic nucleus, nowhere close. In fact, going back on what I said, you probably couldn't see that. What we see when we look from our solar system here, we're seeing either that portion or this portion of the Milky Way. Just a little bit of the band that we live in. That's it, folks. That's all. I don't think we can even come close to seeing that. There's too much in between. Okay? Now, if you took this and rotated it 90 degrees like this, this is how it looks from a side view. Your galactic nucleus is here, and that's lots and lots of stars, and how they're really not all that close together, but they look like they are. And then these spiral bands here, that's what you see going out here. These are coming out of the page, doing like that, with the nucleus in there. Now, what you don't see, remember I said those other things, there are some stars up above this and below it. That's what these are. Now, some of these may be star clusters and other things. The bulk of the stars in the Milky Way are in the galactic nucleus and the spiral bands. But there's a few that are gravitationally attached outside of those. And those are generally globular clusters is what they call them. Star clusters they are. Why they call them globular there, I don't know, but they're clusters of stars that are close enough. Now, so that's the rotating galactic disk, those spiral bands there. Now, the diameter of this, from here to here, from there to there, approximately 100,000, what does LY stand for? Light years. What is a light year? How far light travels in a year. Well, how fast does light travel? 186,000 miles in a second. Okay? Multiply that by 60, you get how far it travels in a minute. Multiply that by 60, you get how far it travels in an hour. Multiply that by 60, you get how far not 60, 24, you get how far it travels in a day. Multiply that by 365 and a quarter or something like that, you get how far it travels in a year. It's a huge, huge, huge number. So for astronomical measurements, we don't use miles or kilometers, we use light years. And this is 100,000 of them. 100,000 of those huge numbers. Okay? That's how far it is across. Now, did any of you like the old series Star Trek? I don't care about these Star Wars things. The Star Trek, you didn't like it or you never saw it. Okay. Remember how Kirk would have Uruhu or whatever her name was call Starfleet Command? And I don't know, were they in a different galaxy or, they were a long way away? Ridiculous. Right? Why? If you were sitting on one of the stars over here, trying to talk with someone in a star over there, hello, how are you today? Okay. 100,000 years later, that sound, that radio signal traveling at the speed of light would reach that one. And, I'm fine, how are you? Another 100,000 years, and you're already dead. It's nowhere close. Nowhere close, okay? Even between here and the closest star, even in our solar system, you're talking minutes to hours for one transmission. Talking star to star, lifetimes. Many, lifetimes before a signal would be sent, received, and come back again. Remember, okay, call me if they come. Sort of like the dumb Yogi Berra. Y'all have heard of Yogi Berra, right? He was a baseball coach who he either was one of the dumbest men that ever lived, or he had the weirdest sense of humor of anyone who ever lived. I heard that he said this. I read it. That for some reason, after he retired, he was getting on up in years, and they were having to make some plans because they had arranged for funeral plots and different things. And his wife said, well, Yogi, if you died before me, which suit would you like to be buried in? The blue one, the brown one, black one? What? Do you have a preference? He said, surprise me. No, okay. It's sort of like that. You're going to be long dead, so who cares, you know? But supposedly he said, surprise me. What's that? I can't hear. Oh, okay, you did? I didn't know that. Wow, amazing. She did surprise him, didn't she? Okay, all right. So anyway, you're talking astronomical distances? Yeah, for sure. Okay, now, that hub, let's talk about that. I'm sorry, the halo, the spherical galactic halo. These stars that live out here, not in the spiral, not in the disk, you know, in the nucleus, but outside of that. This spherical galactic halo contains approximately, that we know of, around 150 globular clusters. Okay? Those are the things you see out there. Now, I'm not good enough at this to know that if indeed we're looking into the spiral that we live in of the Milky Way, and that's what we're seeing there, one side or the other. My guess that most of this that we see here are not those globular clusters. These are stars that are as close to us as these are to each other, but we're right in the middle, so they're around us. So if someone was over there looking back, we would look like this. So I'm not sure we even see those globular clusters. Maybe every now and then one of those is one. If there's only 150,000 and that's scattered over this, we probably can't, 150 globular clusters, we probably aren't going to see many of them. We're seeing, when you look at the Milky Way, we're either seeing that or this, and what we're seeing around that are the stars that are on either side of us within our arm. Okay? Now let's move to other galaxies. Okay? No, let's stay where we are. All right. Our nearest neighbor, actually there is something closer than Andromeda, and that's a local group. It's a dwarf galaxy. Boy, these astronomers, if they don't like something and downgrade it, they make it a dwarf. Okay, this is a dwarf galaxy. Now, these dwarf galaxies are only about 1,000 light years in diameter, nowhere close to as big as we are. They're dwarfs, okay? The nearest dwarf to Milky Way, okay, I meant to say this earlier. Let's go back here. What you reckon's in here? In that center of the galactic nucleus. A black hole, a massive, amazingly huge black hole. In fact, that's probably why it is a galactic nucleus, because it's probably drawn stars, whole stars, in toward it. Now, whether it's eaten any of them up, probably so, but that's why they're there, because it is enormously strong gravitationally. Remember, we talked about black holes last time. That's what's left over from the huge, most massive stars. When they die, they leave a black hole. We don't understand them at all. The reason they're black is because they're not hot. No, they could be very hot. Why are they black? Because light can't escape them. the gravitational attraction is so strong, light gets drawn back in. Electromagnetic radiation gets pulled inward, not sent outward. That's amazing, okay? That's what we form around, okay? So, these other dwarf galaxies are much smaller black holes, okay? And they only gather a few billion or 100 million or something like stars around them, only a mere 1,000 light years in diameter, and the nearest one to us is being disrupted gravitationally by us. Our Milky Way, at so many stars, such mass here in the Milky Way, we're messing with them. So probably we're tearing them apart, okay? And some stars are going to be pulled off, you know, who knows what's going to happen, okay? Andromeda is about 2 million light years away. Now we're 100,000 light years across, okay? So take that and multiply it by 20, and there's Andromeda, okay? 100 million times 20 would be, 100,000 times 20 would be 2 million, okay? So 20 of our diameters away, somewhere there is an Andromeda. But those are huge numbers. It doesn't sound like much there. Very similar to the Milky Way. They are also spiral, you know, galactic nucleus, galactic disk, you know, lots of things are there. Now, the two of us, Milky Way, and by the way, now I've heard this, and I don't understand this at all, but I actually have heard this, that Andromeda and Milky Way, and this, to me, isn't supposed to happen, but they say it might be happening, are actually coming closer to each other. And I thought everything in the universe is getting further apart. So I don't understand the physics of this part at all. But that sometime in time, they may get close enough that they collide? Well, no, there's really so much space between the individual stars, even in that nucleus and everywhere else, there's so much space that more than likely they'll just pass through each other and keep trucking. Now, to me, I don't understand that at all. Seemed like gravitationally that wouldn't work, but that's what I've heard is one theory, that we might actually, not in our lifetime, pass through each other. And, leave that alone. Well, how do we classify galaxies? Hubble, we've seen that name before. Be a good paper topic, by the way. How do we classify? Well, we have several. Some are called elliptical galaxies. Okay? Some are called spiral. Guess what we are? Spiral galaxy. Others are called barred. Now, all I can figure, nucleus here, and then rather than a spiral going around them, you have bars going out of them. That's what my guess is. And then others are just called irregular. They're just hanging around there without any fixed shape. They do have sort of a picture. Oh, this one. That is a space telescope blown up picture of Andromeda. We can't take a picture of us. We can't get far enough away to take a picture, okay? But that's Andromeda. This would be the what? Okay, somewhere in there is a black hole, but this would be the nucleus, the galactic nucleus. And it's sort of hard to distinguish, but these would be there's two names. The spirals and also the galactic, what do you call it? Huh? I can't hear. Remember? Last slide. Rotating disk, okay? Okay, rotating disk, also the spirals. Since it is a spiral galaxy, well, I'm going the wrong way, am I not? Okay, sorry about that. I'll get there again. Sorry, here we go. That's Andromeda, okay? That would be the disk. And then, depending on your perspective of space, if these are in, it's hard to tell whether this is way out there beyond it or is here, but those could be some of the galactic globular clusters. star clusters around there. Okay? Now, my guess is these are other galaxies even further away. I don't know that for a fact, but my guess would be that. Okay, there's a picture of Andromeda. Well, they don't have the picture of the other galaxies. I think your book does. I thought it did. Yeah, no, it doesn't. The older edition of the book did. I'm sorry, this one does not. Has some of those, a representation of those types: elliptical, spiral, barred, and irregular. But just be able to recognize the names. You don't have to draw any pictures. Okay. But Milky Way and Andromeda are both spiral galaxies. All right. Before we looked at the life of a star, now we're looking at the life of a galaxy. And guess what, folks? This is a theory. Remember, theory is a group of hypotheses that people think might be true or happening, but nobody knows. Theories have to be tested. To make it a fact, you would have to experiment with it, test it, see if it, no one's been able to reproduce it to see if this is how it happened. The Big Bang Theory, not the television show. Now, admittedly, the television show is funny, most of it, okay? And amazingly, it has a lot of really good science in it, between all the garbage that's in it, but it does have really good science, okay? Most of what they say about science is really based on science. The rest of it is television. Okay. But the Big Bang Theory is that the universe started from some explosive beginning. Now, we talked about this last time. Sort of problems and not so big problems. I just realized I'm probably interrupting classes all up and down the hall, but who cares? Okay. From some explosive beginning and sent the galaxies flying outward. Now, evidence for this comes from the fact that as we study these galaxies, we see that they tend to be getting further apart. Always. Okay? But then what Hubble discovered, there's his name again, is that not only are they getting further apart, but they're accelerating away from each other. Now, that's the scary part to me, because from physics, I understand the only way you have acceleration is if you have a net force. So it wasn't just a big explosion that pushed them out there and they just are flying along at a constant speed. They're still accelerating. What is that force that's pushing them further and further apart? I mean, just an explosion would push them further apart, especially if there's not that much gravity or friction or anything else to hold them together. But why are they accelerating? The force is still there. Is it with you? Never mind. Okay. Supporting evidence. Okay. Now, they just list the stuff here, and as I say, and I'll say it again and again and again, nothing is going to replace reading the book. Okay? Please don't even try to understand all this without reading the book. In fact, I should have stopped. This is a timeout here. Extraterrestrials, there is a nice little blurb on that. Now, back, a couple decades ago, this was a really hot topic. Remember the movie? Y'all may not. E.T., okay? E.T., extraterrestrials. What's that? Yeah, well, and that's exactly what it was, Hollywood, pretty much. They are trying to figure this out, okay? Read this blurb and you'll see the likelihood is pretty slim. Now, I believe I heard a comment about that maybe Stonehenge was aided in its construction by some extraterrestrials. Maybe, we don't know, but where are they now? I don't know. But that's worth a read. And then I think we mentioned last time redshift and Hubble's law. There's a blurb on that on page 367 or thereabouts. So please don't neglect reading those. And then I'll come back to these other two later. Let's go on with this now. So the universe is, so yeah, where I was going here, you have to read the text to get a little more detail. All it says here, microwave background radiation, number 2, large-scale expansion. You'll have to read the text to get a full description of this. I'll try to do a little bit, at least give you a framework to put this in, okay? If there was a Big Bang, yeah. Oh my word. I guess he didn't plug in. Okay. Oh no. I guess when he was doing all of his work, he accidentally unplugged my computer. Okay. Maybe I did, but I sure didn't realize it. Okay, sorry about that. Okay. All right. Let's imagine there was a Big Bang. Okay? Huge explosion that started all the process. Now, lots of energy would have been sent into space. Okay? Way out. Okay? Now we are where we are. Milky Way galaxy, probably just an average old galaxy, somewhere floating around out there. I don't know how far from the Big Bang or how near. I have no clue on that one. Except that the better we get our telescopes and our detection equipment, the farther out we can see, hear, detect, that kind of stuff. So the farther out it is, that means the longer ago it happened. So the further out we detect, we're that much closer to what happened at the beginning. Now, in my limited mind, I can't see how we can ever tell what really happened, because when it happened, things went out, and those are already way past us. I mean, we're never going to see those. They're gone, okay? So that's what they're doing, though. They're studying some of the microwave, and they're not really that small waves, they're rather long waves, background radiation, trying to piece together what caused it, what would have made that, okay? So that's my best, not a very good explanation of what they're studying there. Large-scale expansion, that's what I've been talking about before. We do know, as we study things, we sense they're getting further and further apart. Relative abundance of the elements, okay? We talked about this before. Remember we said that the fusion of hydrogen to helium, and then if you have a bigger star after all the hydrogen's gone, if you have enough helium, when it has a gravitational collapse, then the helium fuses to carbon. And then if that's big enough and hot enough, and when it collapses again, it may get hot enough to fuse carbon to bigger and bigger molecules until you get to iron. But when you get to iron, that's about it, folks. And I mentioned on the periodic table that iron is only number 26 out of 103 or so that we've named, 118. We haven't named them all, but somewhere up there between 92 is uranium. That's about the largest naturally occurring one we found, up to 118. Speculating they have them that big. Relative abundance. Where are all these others coming from? Some pretty major supernovas that were bigger than normal collapse, okay? So the relative abundance of those elements indicate you had to have a pretty big bang to create things larger than iron. 26, okay? So atomic number 26. So that's another evidence that something really big happened, okay? Now, this goes back sort of to this one. Diffuse cosmic background radiation, okay? Again, the sensors we have, the farther out we can see, the farther back in time we are looking at and studying these things. That sort of low energy, high wavelength, long wavelength, this is high energy, shorter wavelength, studying them as well. And one of the things that have done this is the Kobe spacecraft, okay, that's out there still collecting data. By the way, all these are good paper topics. Tell me about the Kobe spacecraft. That may be fascinating in itself. Now, here's the question. Where do we go from here? Okay? If there was a Big Bang, okay, obviously it just didn't get over with because the Big Bang, we're still accelerating outward. Can we do that indefinitely? Or if at some point, is it going to slow down enough to be constant speed and not accelerating? Or does it actually start coming back like a bungee cord? Does it actually start coming back and you have a big crunch and we start all over? In fact, could we be in the 74th cycle of crunches and bangs? You know, we don't know. You know, we have no clue. Okay? And it's all speculation about where we are there. But it's interesting speculation. Good things to think about and study. Now, okay, I guess I ought to do it now. I was sort of trying to avoid this till later. Time out again for a blurb alert, okay? On page 368 or somewhere thereabouts, you'll see a blurb, a closer look, they call it, on dark energy. Strange name. What do we mean by dark energy? Well, light energy is energy that's emitting at frequencies that we can detect. Okay? Dark energy is generally pretty low-level energy that we're not detecting. Okay? Or we have a hard time so far detecting. And the strange thing is they have evidence that there's probably more dark energy out there than there is light energy, okay? I'll let you read this to get the full story, but let's go back to a very small scale, like us on the Earth, okay? We can have nuclear explosions, you know, as in power plants and submarines and aircraft carriers and things like this, or nuclear tests and things like that, North Korea, okay? Or we can have fires and burning things and all sorts of things of energy. But where does that energy go? Ultimately, it dissipates until it's low-level heat energy. In fact, some people say the universe will die of a heat death. It sounds like it's hot or something, but actually heat is a pretty low-level energy. You don't see heat. You have to have infrared spectrometry to see heat. It's really long wavelength, low energy, and that's what it all tends toward. In thermodynamics, there's 3 laws. The second law in thermodynamics says everything tends toward randomness. That's one way of expressing it. Entropy increases, okay? Randomness increases. And that's the same thing of saying heat death of a galaxy, okay? So dark energy, to me, is a result of entropy taking over, you know, things tending toward randomness. Read the blurb, see what you think about it. That thing I was saying about Hello Enterprise, okay, that's on page 368 also. This is just an example. What's the closest, now not the moon, the closest planet to us? Mars, okay? If we were to call Mars and say, hello Mars, how are you doing today? At the speed of light, those radio waves would take 4.3 minutes to get there. And another 4.3 minutes to come back, okay? So that's not a very reasonable conversation. It's sort of like when I ask a question in class. No, I'm sorry, that's not a thing like that. Okay, now, if if Star Trek, the television show, had really had that, and Captain Kirk had said, Uhura calls Starfleet Command, it would have been several episodes later before Uhura said, oh, they answered to Captain Kirk, okay? Certainly wouldn't have gotten it done in a half hour or an hour, okay? Jupiter is not the next closest, but it's going from us to Mars. Let's go to Jupiter. Actually, to correct ourselves, I think Venus is a little closer to us than Mars, but let's go outward. Mars is the next closest going out. If we were to call Jupiter, how long would it take? If you got your books, you see 35 minutes for a one-way. If you flash the light signal to Jupiter, it's going to take 35 minutes for that light to get there, okay? And another 35 to come back. That would be a whole show, wouldn't it? Okay. Saturn, the next closest planet going outward, 1.2 hours for one signal. Speed of light. This is in our solar system, okay? Uranus, 2.6 hours. Neptune, 4 hours. Pluto, on average, about 5.3 hours. What's wrong with that graph there, or that statement? Pluto is no longer classified a planet. What do we call it? A dwarf planet. We call everything something smaller. Across the Milky Way, 100,000 years. To Andromeda, 2 million years. Okay. Civilizations die much quicker than that, okay? Now, I think one of the weirdest things about thinking about these distances and times that is so strange for me to think about, I remember thinking about this as a child when I first heard it. I'll look up there and see a star, realizing that star is how many 1,000 light years away, and realizing that star may not be there anymore. In those 1,000 years, it could have exploded, okay? It could have died, okay? And so I'm looking at the light that it produced 2,000 or 3,000 years ago. That's what I'm seeing. I'm not seeing the star as it is today. It may be gone, absolutely. So that's what I say. Civilizations die faster than this, okay? Now, if you thought dark energy was strange, try dark matter. Almost a whole page of a blurb on that. A closer look, they call it. Now, what do we mean by dark matter? Well, say again? Okay, no, not even that. Though that is pretty dark, I would think. But this is matter that's out there we can't see. We can only see stars because they're hot enough to be emitting light, electromagnetic radiation. Or even if they're not hot enough anymore, they may still be doing electromagnetic radiation that some of our really sensitive telescopes can pick up. But you know, most of the universe, the real substance of the universe, is not emitting anything. And we don't know how much of it is there. The best we can do is measure gravitational fields and realize that some things are operating in rather strange ways, and the only explanation is there's some sort of matter out there that's attracting them. But it's not massive enough or hot enough or anything to be cement. So there's a lot of matter out there we don't know even how to classify. They call it dark matter. Now, certainly a black hole, to me, is dark matter too. I'm nowhere close on that either. I mean, even further away from that. So there's a real good blurb on that. Well worth a read. Now, if you choose to write a paper topic on dark matter, remember this is not your source. You have to have sources outside the book, or dark energy or anything else. These give you ideas. You have to find sources outside the book. Okay, now why do we have raisin bread? Why is that on our slide when we're talking about the galaxy? Well, this is actually one of the early astronomers' model that he used to talk about the universe. We could tell the galaxies are getting further from each other, And he said it's a lot like raisin bread. You have the galaxies in some sort of fabric of space, and the yeast is making them expand. So at one time, the raisins were 5 centimeters apart, 1 centimeter apart, and 16 centimeters apart. And sometime later, they were 2, 10, and 32 centimeters apart. And they're all moving away from each other at a fairly regular and systematic pace. Now, that to me is why I say, how can Milky Way and Andromeda be getting closer together if the galaxies are supposed to be moving further apart? I don't understand that one, except maybe we're such big players that we don't even count. The big ones are doing, this kind of stuff. I don't know. The scary part of this is the bread is rising at an increasing rate. It's not just increasing slowly, increasing ultimately to stop. It's increasing as in it's about to blow up. I mean, it's like it's still blowing up, which is sort of scary to think about. Okay, another way to look at that then is that if sometime way back there was a Big Bang, then, and it formed, and this is just 4 representative galaxies, it formed billions upon billions of galaxies, that they are moving further apart, and sometime in time they were here, and some later time they were here. They're moving away from the Big Bang, but also moving away from each other. Okay? That's the deal. And so far we're still moving away. Will that rate of increase slow? We don't know. We haven't studied it long enough to know. And start coming back, actually stop, and then start coming back and have a big crunch? Anybody's guess. Way beyond my pay scale. Okay. That's the last slide in chapter 14. Okay? There is yet another blurb here. This is People Behind the Science. And every chapter has at least one of these, if my memory's right. And this one is on Jocelyn Susan Bell Burnell. I don't know why she had to have so many names. Now, at the time of the writing of this book, she was still alive, but she's on up there, okay, in age. Born in 43, which is 6 years older than my brother, so yeah, she's in her 70s if she's still alive, okay? Maybe close to 80s. No, she'd be, oh yeah, 80, I can't add, terrible. No, 73, 74 now, okay. She was a British astronomer. I'm not going to read the whole thing, but she was the first, catch this now, there weren't that many women astronomers, but she was the first to see a pulsar, identify and realize what it was. We talked about that earlier, a pulsing star. And since then, many others have now learned to look. But in reading the article, remember, this can't be your paper source. You can write on her, but you got to get a source outside the book, not this. I've read this, I'll recognize it. But you'll find there's several other names mentioned here. James Clerk, it looks like it's Clark, but it's pronounced Clerk Maxwell. They named a telescope after him. You can write on him or his telescope. You can write on the observatories. You can write on several things there. You can write on what pulsars are. I mean, you can find several potential paper topics just in that blurb, but the blurb itself is well worth a read. Now, as an illustration of what I'm talking about, nothing replaces reading the chapters. When I first came to what was then Bessemer State Technical College, this building, this campus was that, I was hired to teach math and physics, okay? And my background was physics and math, okay? Fine. But then when we merged, or in the process of becoming a community college, that was the original plan, we found out the physics we were teaching wasn't transferring to four-year schools, and we wanted to have college transfer programs. And I talked with one of the other physicists that I know, He said, look, what you're teaching in physics now, that's in Physical Science 112. Why don't you teach physical science, not physics? That transfers, the low-level physics. Now, the physics we teach here now does transfer. But we weren't teaching this back then. So that convinced us to go to physical science. Except physical science had 1 and 2. 1 was physics and 2 was physics and chemistry. 1 was astronomy and earth sciences. Earth sciences, no problem. I did research on soils. No problem there. It was the astronomy part that scared me. I had never taken an astronomy course in my life, and I was going to be teaching astronomy in physical science. So I literally, it wasn't this book, it was an earlier edition, I took the book home every night and read as much of that chapter every night as I could, and when I finished it, I'd start over again. I had to literally read the chapters, parts of them, several times before I felt comfortable even teaching it, okay? So this is a pretty good author, but frankly, I didn't get it on the first reading. Not all of it. I got the bulk of it. So nothing replaces reading the chapter. Not the PowerPoints, not all the little things I tell and the stories and the blurbs and stuff. Nothing replaces reading a chapter. Please read the chapters. And once you've read the chapter, then at the end they have a summary, which does a fairly good job of summarizing, hitting just the highest of the high points, but it does miss a lot and skips a lot. Then they have key terms. I'm talking about page 372 or thereabouts now. And this chapter has about an average number, quite a few. They list them alphabetically, but they put in parentheses the page number where they're found. So if you see the thing and say, oh boy, I remember talking about it, but I don't remember what that is, you can go to that page number. The next thing they have at the end of the chapter is something called applying the concepts. These are multiple choice questions. This chapter has 50 of them. That's pretty close to average, maybe a little above average, okay? And then they have the answers. If I were studying for a test, which, hint, hint, you're having one next time we meet, I would definitely look at these applying the concepts, okay? Now, I'll guarantee you this, none of the test questions are going to be the same as these. But the test questions are going to be based on the same material as some of these. So the questions may be phrased differently, asked different ways and stuff, but if you can go through and do this applying the concept, figuring out what answer you would have, then compare it to the answers here, figure out why you missed the ones you missed. If you can't figure out why you missed the ones you missed, ask me in class next time, okay? Ask me during office hours. We'll go over any of those that are puzzling to you, okay? But if after a while you get those down, you're going to have a really good probability of doing quite well on the test. Because your test is going to be mostly, in fact, the first test may be totally multiple choice. Again, not these questions, but the same material that is covered in these questions. Then the next thing they have here is a group of questions called questions for thought. 21 of these. This is probably a few more than most chapters have. If you think through these, understand what they're asking, generally what the answer is, read the book, whatever, I think you'll, again, that would be a very good thing to do. For further analysis, they only have 5 of these. Most chapters have maybe a couple more than that. Okay, and then there's another invitation to inquiry that you can read. I think it's basically, no, it's something else. It's a spacecraft that we sent up there, and it just keeps going, okay? And it's still sending us data long past where we thought it would. Okay, so anyway, those are one. Now, the last thing they have in each chapter are what they call parallel exercises. And the examples that we've had in the text that I've sort of read through and talked about, but we haven't actually done, mostly are based on the chemistry and physics chapters that we haven't had. That's why I sort of breeze over them. So most of these parallel exercises are based on those, but some of these you could probably figure out answers. Probably not going to have anything that complex on your test, but if you want to really understand the material well, those would be worth looking at. Now, if any of you do have the big book, the parallel group A exercises, answers are in this, all of them. The group B are not. But that's the second thing they did poorly when they extracted the chapter, what do they call it, customized text. They didn't put the answers in. Sorry about that. If any of you are that interested and want to see it, I'll make you copies of the answer if you're interested in seeing the answers to the parallel exercises group A. All right. Any questions? Chapter 14. Yes? Yeah, it's strict. It's just on 14, not anything we cover in 15. Okay, though when we start in 15, you'll see it's repeating a lot of concepts and things. So actually 15, in some ways, be a little bit of a good review of what we did in 14 too. It all builds on itself. Now let me say this too. Every test you take in here, every chapter test, the final exam at the end, you can have a formula and equation sheet. Anything you want to write on a piece of paper, front and back, however you want to do it, in front of you. So I don't believe in memorization. I believe in understanding concepts. So if there are any facts and things like this you don't really want to sit down and try to memorize, I'm not a good memorizer, that's why I don't do it. Write it down on a piece of paper. And frankly, things that you see when you read through those study guides at the end, the questions, the things, you'll see a lot of things being repeated. If you see something repeated a lot of times, say, it may be important. So let me jot those down. So I'll let you figure that out. And let me do a little timeout here. When I was in college, yeah, do you have a question? Oh, okay. Yeah, I understand. When I was in college, very seldom did I have a professor who let us have or encouraged us to have formula and equation sheets. But I did have a few that did allow those. And here's what I discovered. Way late, it was upper level classes by the time they did. I wish I had known this when I was younger. When they allowed those, boy, that night before I went through those sections or chapters or whatever it was, finding what I thought was the most important facts, writing them down, putting things down in an order that I could follow, and making it so I knew how to figure out where the process and progression was here, so I would know where to look when I was looking for this. And then I'd go down to sit down and take the test. I'd forget to look at it. I found out that was the best study technique I wish I'd have known about before. If you write down a formula and equation sheet, you see, reading something, that's learning. Writing is more active than reading. Reading is sort of passive. Writing is active. Listening is very passive. That's why I say read the book. That's more active than listening to me talk about it. It's more active than watching a slideshow. Writing down, putting your thoughts together, organizing, figuring out what's important and what's not, that's really active learning. You're going to learn it far better that way. So I would say every test you ever take, do a formula and equation sheet. If the subject fits, do it. Whether you can use it or not, it doesn't matter. Do it the night before. Don't take it in if you're not allowed to do it. But just the fact that you've done it is probably going to give you a boost on your score. I can't guarantee it, but I would say real good chance of that. Okay. Enough of that. Any questions? Chapter 14. Goodness, it's hot in here, or maybe I'm just full of hot air. I don't know. Okay. Now, I've got that it's right around 2:15, 2:16. At 3 o'clock is when the theory part ends and we begin the lab. So we've got about 45 minutes of theory. You want to wait till the 3 o'clock witching hour to take a break, or you want one now? You need one sooner? You okay? Well, maybe we'll need one just to get PowerPoint to load. I don't know what the story is here. This is a bigger file than the last one was, but man, that's taking forever to load. think I ought to stop it and try again. Isn't that exciting to watch? Okay. Sometimes this will jog its memory. Not responding. So I think what I'm going to do is end. And try it again. What would you say? I would say no. Let's see what happens. I don't even know what safe mode is. What is it, you know? There it is. I figured just shutting it down might work. Okay. Okay, at least one person did take me up on the time for a quick break. Does anyone else need one? Okay. All right. Okay, we do have some takers. Okay, I'll pause this just briefly. Would you like me to wait till she comes back, or are you okay? Yeah, fine. Okay. Poor Shelby, she's out in the hall. She was starting to come in my office, but I jumped in my office. I was just too hot in here. I took off my T-shirt. I told my work study student, gross him out, but he was doing this. I thought he was telling me to get out of the room. But he was telling her not to come in the room, okay, because I was in the middle of taking my shirt off, okay, but it's back covered again, okay. Ugly thought, right? Okay, we move on to chapter 15. I recorded all that, by the way. Why, I don't know. Chapter 15, we started with the universe, and now we're going to narrow down to the solar system. Next chapter, we get down to Earth-Moon system, okay? So we're getting smaller as we go. And then subsequent chapter, we focus on the Earth more and more and more. So let's now move to the solar system. Okay? The core concept here, and by the way, in the text, I may not have mentioned it last time, I don't know why they do this, and maybe different texts are different ways, but mine, they put the core concept, which to me should be the most important thing out there, they put it in white print and with a yellow background, which makes it really hard to read, okay? But here it's a lot easier to read. The solar system is composed of Sol, S-O-L, the sun, okay? And the orbiting planets, and dwarf planets, and smaller solar system bodies. And that's basically the organization of the chapter. I'm not going to really do too much with the sun, except maybe look at size and stuff like that. But most of this chapter is going to be the planets. All 8 of them, okay? Well, not really the Earth. That's going to be the next chapter. Then we'll mention, just really briefly, some of the dwarf planets and why they're dwarf planets and not other planets and so on. And then we'll look at the smaller solar system bodies. Can anyone name those right off the top? What are some of the smaller solar system bodies? Comets, asteroids. Those are the major ones. Okay, comets, there's actually 2 types of comets, so we'll go over that too. Okay, so let's start with the sort of the introduction, background type thing. 15.1. I don't want to skip. Yeah, okay. I'm trying not to skip some pretty important facts here that I don't think show up in the slides, so just seeing where they fit here. The International Astronomical Union, the IAU, that's not International Auburn University, by the way, it's just IAU, Astronomical Union, is the governing body over the names of celestial bodies. Okay? By the way, they do lots of things, like they determine what the different mountains on the moon are named. You know, some people say, well, let's name one after Joe Blow here because he did this. So they do the name. They also define what is a planet. And if it's not quite meets the definition of a planet, then is it a dwarf planet or something else? And what are the smaller solar system bodies? How are they classified? That type of thing. So the IAU governs all those kinds of things. And in 2003, that august body determined that Pluto did not meet enough of the qualifications or the specifications needed to really call it a planet. So they downgraded it to a dwarf planet, according to the IAU definition. They set the definition, then they determine who meets it. Now, the book doesn't go into enormous detail on some of the things that didn't. I'll just give you a few reasons that Pluto was downgraded. Basically, a planet needs to be pretty close to spherical in shape, okay? Our Earth is not a perfect sphere. It's an oblate spheroid. We'll do that in the next chapter. We'll talk about what that is. But it's close enough to a sphere. Actually, Pluto, not really all that spherical, okay? It is somewhat, but not enough. Another thing that a planet needs to be. Planet needs to have, that none of the planets have perfectly circular orbits. They're all elliptical orbits, but they're not far from circular. Except Pluto is way out, okay? In fact, back when we called Pluto a planet, we said Neptune and then Pluto, right? Because of distance from the sun. But what we were talking about there was average distance to the sun. Actually, Pluto's orbit was so elliptical that for a small part of its cycle around the sun, it was actually closer to the sun than Neptune. Other times it was way past. On average, it was out there, okay? But sometimes it was close. So it had a more elliptical orbit than the planets did. And the other thing to me that really was bad, remember we talked about the galactic disk, okay? You had a galactic nucleus and then the things around it, the disk, okay? Well, the sun's that way and the planets. It's not that the sun's here and Mercury's here and Venus is here, and they're not just all over the place. They're all in pretty much of a disk. Not a perfect disk. Mercury is a little off. Everybody's a little off by a little, but not by much, within certain bounds. Pluto, like 17 degrees. Everything else is like no more than 4 to 5, 6 degrees off the norm. Pluto's like 14, 17 degrees off. So there were several things like that. And there are some others the book will mention. We'll get to those in time. Okay? So it was downgraded. Okay? So let's look at, like I said, the solar system. Now there's a couple of concepts here that I want to make a big deal about because there are things that have given students problems in the past, and I want to make sure you understand. The solar system, again, S-O-L, when you see that, think sun. That's what that root means, the sun. Sol, good old Sol. The solar system consists of our sun, our unitary sun, 8 planets, not counting Pluto, that's the 9th, used to be. Hundreds of moons, okay? Jupiter itself has, I think, more than 60 or 70 moons, okay? So somewhere in the neighborhood, but more than 100 moons. Thousands of asteroids, millions of icy bodies that could, some are comets and some are not, and they don't even mention the dwarf planets, okay? I do want to mention them, okay? In the text, there is a definition. A dwarf planet, okay, let me back off a little. A classical planet, to be a classical planet, an object must be orbiting the sun, nearly spherical, large enough to clear all matter from its orbital zone. Okay? Spherical, Pluto not as good as it should be. And it says orbiting the sun. Well, just about everything orbits the sun, but in a nearly circular orbit. That's what they're meaning. Pluto's is not. It's way too elliptical. All of them are elliptical, but theirs is way out. So that's one reason. So the dwarf planet is defined as an object that is orbiting the sun. Everything orbits the sun. Is nearly spherical, okay, but has not cleared matter from its orbital zone and is not a satellite, okay? All other objects orbiting the sun are referred to as small solar system bodies, okay? Now, that sort of says the same thing I did. I hope my definition may have been a little clearer, but maybe not. In the next paragraph, I wanted to say, certainly Pluto is now a dwarf planet, but, okay, here's another. The old definition of a planet was anything spherical that orbits the sun, which resulted in 9 planets, okay? But then a new astronomical body was discovered. That body was named Eris, E-R-I-S, okay, after the Greek goddess of discord, okay? Eris was larger than Pluto, round, in other words, more circular probably than Pluto. It circled the sun, but if it was going to be a planet, there were problems, okay? Well, guess what? Then they discovered, well, they already knew about an asteroid called Ceres, C-E-R-E-S. That would mean Ceres would also be a planet. But then when they did that, they found out there were probably 50 or so large icy bodies believed to be orbiting the sun far beyond Pluto. They had very elliptical orbits. They were sort of, yeah. So soon the whole Pandora's box was open, and everybody was wanting to be a planet. And they obviously, no, they just weren't in the same league. So when they had to start throwing the others out, especially Eris and Ceres, they had to basically get rid of Pluto too. So the reason I did that is so you'll focus on there are other dwarf planets. It's not just Pluto. Eris and Ceres are also, and then there are others as well. Now, here's one. 5 dwarf planets. The last part of that paragraph. Pluto, Eris, Ceres, Maki. Almost sounds like a fish or something, doesn't it? Okay, M-A-K-E, M-A-K-E. And Haumea, H-A-U-M-E-A. I'm not even sure of the pronunciation. And many, many more small solar system bodies. So now we know of at least 5 dwarf planets. Not meeting the criteria that we use for planets. Okay. Okay. Now, let's talk about just some nomenclature here. So later when we're talking about things, we'll know what we're meaning. Okay? First, this is Auburn University. It's close, but it's not. It's an astronomical unit. An astronomical unit is defined to be, and this is only basically used in our solar system nomenclature, okay? Astronomical unit, okay? I think we should have used something like a solar unit or something, but it's an astronomical unit, okay? It's the average distance between the Earth and the Sun. Now, here they give it as 1.5 times 10 to the 8 kilometers, okay? What that means is 1, 5, 0, comma, 0, 0, 0, comma, 0, 0, 0, okay, kilometers, okay. Now, the number I remember more, because I'm used to the U.S. customary system, about 93 million miles, okay? This is about 0.6 times that, so 93 million miles is the average Earth-Sun distance, 1 astronomical unit, okay? Otherwise, we'd be talking about exponents that are huge. So let's just do 1 astronomical unit. Now, the planets. That's where we're focusing. That's where most of the chapter is. The 8 planets, classified according to size, density, and atmosphere. Okay? Now, some of these things interrelate and some don't so much. When we're talking about size, here's a generalization that's true. The smaller planets are your denser planets. So these are related to each other. Okay? The larger planets is really kind of hard to say what's atmosphere and what's not. Okay? So anyway, these are our planet classification scheme. But then you turn around and look at this, and there really is a bigger classification scheme. And what that is, they're terrestrial planets, and then they say giant planets. Most books call them the gas giants. And there's a reason for that. What in the world do you think we mean by terrestrial? Say again? Rocky. Excellent. That's exactly it. Stuff like the Earth is made of. Rocky. Okay? Mercury, Venus, Earth, and Mars. Those are the 4 terrestrial planets. They are the smallest planets, but they're also the densest planets because they're rocky. They're solid. Okay? That's what they are. Mostly, well, you read the thing, didn't you? Okay. Now, mostly rocky materials. Most of that is metallic, metal, nickel, or iron. Wait a minute, I don't know where there's that much nickel and not really all that much iron. I know around here there's a fair amount of iron, but I thought we were quartz and granite and stuff like that. Why does it say we're mostly nickel and iron? Okay, we'll do this in the next chapter. We live on the crust. The crust is like the skin of the earth. That's as deep as we go. We don't even go skin deep. The interior is mostly iron and nickel, okay? But we don't ever get, I mean, I'm not talking about drilling a well. You're still in the crust there, okay? I'm talking about going way down deep. We're mostly iron and nickel. Okay, that's the terrestrial planets. 4. Small but dense. Having maybe atmosphere or not. In other words, Mercury not, Mars not much, Venus too much, Earth, yeah, just right. Okay. Then we have the giants, and just not calling them giants, the gas giants. Jupiter, Saturn, Uranus, and Neptune. Okay? Why do I say gas giant? They're mostly hydrogen, helium, and methane. 3 gases. Okay, 3 gases. Now, does that mean there's nothing solid about those 4 planets? We don't know for sure, but we're guessing their core has to be solid. And they may be iron and, more like our whole cores are, but they're mostly covered with these gases, hydrogen, helium, and methane. Huge, and when I get them out there, please look at Space Objects in Perspective. It'll be a file in content. Look at that. It's pretty incredible. Okay? Someone did a pretty good job there. Now, well, they had to put it out here. I don't know why. Pluto is no longer considered a planet, but it's a dwarf planet. Now with 4 others, Ceres, Eris, Makemake, and Haumea, or however you pronounce it. Sounds like a volcano in Hawaii or something. I don't know. Now, this is a pretty picture, I'll admit that. But I think it's a deceptive picture in many ways. Can anyone think of a way that's deceptive? Say again? Or in a line, and you never, ever, ever, ever will see all the planets in a line, nowhere close to it. Nowhere close, okay? Anything else deceptive about it? Okay, yeah, they look like they could be perfect circles, and you know they're not. Now, maybe someone say they really are slightly elliptical, you just can't tell. But yeah, that's another. Perfect, very good.
They're all round.
Okay, and well, all the planets by definition have to be spherical, so I'm not going to fault them on that too badly. Okay, here's a couple more you may not realize. What's that? Okay, Pluto's still up there. That's a really big one, okay? Okay, what were you saying?
There's nothing else besides planets and Pluto, basically, and the sun.
Okay, that's all it's showing, but that's all they're focusing on. They do show the asteroid belt here, and that is in the right place. But here is the things that I have real big problems with. The planets, their relative sizes are pretty good. Pretty good. Not quite, but pretty good. Okay? The sun just looks maybe 1.5 times the size of Jupiter. Nowhere close, okay? If that was really the sun, it would be taking the whole thing to these would be little specks way out there. So the relative sizes of the planets are fine, but not with the sun. The sun size, nowhere is much magnitude bigger than that. And here's the other one. And maybe this is what y'all were meaning before. These look like they're relatively the same distance apart. Nowhere close. Mercury is much closer to the sun. And then basically, this is just a rule of thumb here, Mercury to Venus, there's almost twice the distance between Mercury and Venus as it is the sun and Mercury. Again, twice that to here, twice that to there, twice that to the asteroid belt, twice that to Jupiter. I mean, you're getting much, you couldn't even get this on the scale and get anything close, okay? And then one more, and this is not very fair because they weren't really focusing on this, but our moon is almost equivalent to the size of Mercury. And that size is not the scale. And I'm almost certain this is true, that our moon, I think, is actually larger than Pluto. Okay? It's not really a planet, it's a dwarf planet. There are 4 big moons in Jupiter. You can't see them all because we got Saturn too close. And at least some of those are bigger than Mercury and Pluto. And there's at least one huge moon on Saturn that is bigger than Mercury or Pluto. And I don't see, I mean, that one may be close to the same size, but I don't think quite. So there's some little things like that. But they're just trying to show the planets, but they got the relative spacing wrong. Just the planets, the relative sizes aren't bad, but the sun's relative size, way bad. Okay. Yeah, y'all hit most of them. Good deal. Now let's look at each one of them individually. Now, I would have to go to the end, and I don't like doing that. The book, which I like, gives you this table, 15.1. It's on page around 382 or so. While you're still talking about Mercury, right in the middle of that. And this table has tremendously great information in it. I mean, fabulous information, okay? And the slide set either skips the table completely or puts it at the very end. I like it at the beginning. So I want to focus on that for just a moment before we start doing the individual planets. Now, there's too much data here, and I'm not going to do everything, but just some of the information. You can either look at the distances in millions of kilometers or in astronomical units. Astronomical units, a bit nicer scale, okay? Mercury, 0.38, about a third of the way between the sun and the earth is Mercury. So it's pretty close to the sun. Venus is more than twice as far from the sun, okay? In other words, double Mercury's radius and you got Venus just about. Earth is 1 astronomical unit, that's how we define it, of course, But you see, we're far closer to Venus than, let's see, is that right? Yeah, we're closer to Venus, about the same, as Venus is from Mercury, okay? And Mercury from the Sun. So far, pretty evenly spaced, okay? But then when you go to Mars, you're another 50% further out, okay? And then you go to Jupiter, and look what happened. You're more than 3 times further out than Mars was. So you've gone from something on the order of 1, less than 1 to 1.5 astronomical units for the first 4. What are the first 4 called? The terrestrial planets. When you get to Jupiter, you're way out there. I mean, it's between 3 and 4 times further from the Sun than Mars is, okay? Just a big jump. What's in between Mars and Jupiter? Asteroid belt. So there's a theory there, and we'll come back to that a little bit later, okay? And then when you go between Jupiter and Saturn, you almost double again. And when you go Saturn to Uranus, you more than double again. And when you go from Uranus to Neptune, it's not quite doubling again. So every one step of the way, you're almost getting twice as far. I mean, as it was for the whole thing. Not same distance apart, far, far greater distances apart. Okay? That's what I was talking about there. Now here is the inclination to the ecliptic. Now what is the ecliptic? What word do you almost see in that word ecliptic? Eclipse. What is an eclipse? Okay, when the sun, moon, and earth line up in a certain way. If the sun is in between, no, let's get it right. If the moon gets in between the sun and the earth, we call that a solar eclipse. If the earth gets in between the sun and the moon, it's a lunar eclipse, okay? So in other words, they line up, okay? So what the ecliptic is the path that the planets take around the sun, okay? That's called the ecliptic, when they line up. And notice here, we're saying the earth revolving around the sun, we're going to say that is perfectly 0 degrees. That's what we're referring to our eclipse, the solar eclipse, the lunar eclipse, that's where we are. Okay, now look at Mercury. 7 degrees out of alignment, okay? 7 is pretty high, but remember Mercury is so close, it doesn't take much to be 7 degrees out of alignment. Venus, 3.4 degrees, about half of that. Mars, 1.9, and then from there on, they're pretty small. In fact, Mars is fairly small. Okay? Of course, the further out you get, now, if we had Pluto in there, can't remember for sure, it's something like 14 or 17 degrees. It's nowhere close to the same plane we are, and all the other planets are. Okay? Revolution period. Okay, that's not how often they revolt against each other, though this is a time around the sun. Some pretty interesting facts here. Okay? Of course, you would expect the closer planets to go faster. Doesn't take them as long to get around. They're not as far to go, right? So these are in Earth years. Revolution of Mercury around the sun is about a quarter of an Earth year, about 4 months. Okay? Venus, a little over half a year. Okay? Earth, of course, is 1 year. Everything's based on the Earth. Mars is almost twice as long, 1.8 years. Jupiter, 11, almost 12 years to go around. Of course, it's so far out there, it takes a long time. Saturn, almost 30 years to go one time around the sun. Uranus, 84 years to go around the sun. And Neptune, 165, almost doubling again every time. Okay? How about the rotation period, the spin cycle? Okay? How long does it take Mercury to spin. How long does it take the Earth to spin? 1 day, 24 hours. Mercury is lazy. 59 days. Now look, going around the sun, it took 3 months. To spin one time, it took 2 months. Okay? So really, it's almost spinning as fast as it's revolving. So in other words, its day is almost as long as its year. Okay? Rather strange. Okay? Uh-oh. Anyone see the table? What do you notice about Venus? What's that?
Spinning in the other direction?
Yeah, Venus is spinning backwards. Spinning backwards. And it's spinning back. In other words, if you lived on Venus, you're a weird dude. Okay? No, you'd be dead, so you wouldn't be living there. But if you're on Venus, the sun rises in the west and sets in the east. Okay? It's spinning backwards. Okay? Everything rises in the east and spins in the sets in. But it takes 243 days for Venus to spin one time backwards. Okay? Our days. Okay? Now catch that. That is more than 2/3 of a year. More than 2/3 of a year. More than 8 months. But how long did it, what was its revolution period? 6/10 of a year, which was 7 months maybe. So basically, Venus's day is longer than its year. Okay. Doesn't make a lot of sense, though. Now, I think in one of the trips that we did to the planetarium, and by the way, those people who weren't here the first time, we do have, I have 2 field trips planned. That's stretching the word a little bit. I'm hoping to do 2 field trips. When we finish these 3 chapters on astronomy, 14, 15, and 16, and finish the labs on those, then we're going to take a field trip to, hopefully, to Samford University where they have a planetarium. Okay, and I'll check. I believe they do have wheelchair entrance and things like that. So we'll see what we can work out with that. Okay, I believe it was on one of those field trips that Mr. Weigel, I believe it was, or the guy that was before him, Mr. Axel or something like that, that said there was a theory that perhaps some major something or another collided with Venus and was so disruptive it made it spin backwards. Now that's an interesting theory because there's also another theory that our moon came out of our Earth, that there was some big collision and split off part of the Earth and sent it out there and made it our moon. Okay? And if those 2 things happened around the same time, there were some major problems going on at the time. Now, this would have been very, very, very early in the formation of the solar system, back when we probably were called protoplanets, not real planets. So this was way back in the beginning. And we'll talk about that later in the chapter. Not that particularly, but that. So anyway, Earth, of course, is almost 24 hours to spin once. Mars, interestingly, just a little over 24 hours to spin once. Jupiter, huge thing it is, almost 10 hours to spin once. Saturn is 10.5 hours to spin. Uranus, almost taking after Venus here, it spins backwards too. Now, I think Uranus, if I'm not mistaken, it's hard to say whether it's spinning back. It is spinning backwards, but Uranus, most of the planets in the solar system, our Earth doesn't sit upright. We have an angle, okay? About 23.5 degrees. We'll talk about this later, okay? 23.5 degrees. We're not quite standing straight up. What's the ramification of that? The what? Yeah, the sun hits things differently, and that's why we have seasons everywhere except near the equator. Okay? That's why we have fall spring. Because when we're facing the sun, we're in our summer. And when we're not facing the sun, we're in our winter. And when we're in our fall or spring, we're about equidistant. Okay? So it accounts for several things. Well, all the planets are sort of, none of them spin right upright. Uranus, I think it is, spins almost like this. Okay? I don't know what it's like there. Almost revolving around the sun gives you sunrises and sunsets. The spin just makes the sun do other things. I can't imagine what it would be like there. But also Uranus spins backwards too. Not as slow as Venus. It's about 17 hours, and Neptune is about 16 hours, but spinning in the correct direction. You know, when you look at these two, they're almost twins, except they're diametrically opposed in many ways. One spinning one way, one another. Yeah, strange, but true. Okay. Masses, Mercury, about a 20th the size of the Earth. Okay? Venus, almost Earth size, 4/5 the size of the Earth. Earth is Earth size, okay? Mars is down there just about twice as big as Mercury. Not very big, 1/10 the size of the Earth. Jupiter, 318 times the size of the Earth. Saturn, 95 times. Uranus, 15 times. And Neptune, 17 times. Again, those two are almost twins. Okay? Equatorial dimensions, this is how big our diameter is. Okay? But let's do it in Earth radii. Okay? So this won't be diameters, this would be radiuses. Mercury is a little over 1/3 of the radius of the Earth. Much smaller mass, but only 1/3 of the radius. Venus, almost the same, 95% of what Earth is. So that means her mass was 82%, and the radius, though, is 95%. She's not quite as dense as we are. Is anyone as dense as we? No, I'm sorry. It's really true, though. Okay, Earth is a radius of 1. Mars, about half of the Earth radius, much smaller. Jupiter, 11 times the mass, the radius of the Earth. Saturn, 9 times, and Uranus and Neptune, 4 each. They're almost twins. Okay. Atmospheres. Basically, Mercury has no atmosphere. Okay? Now, down here, you see, I'm going to pick on Mercury now, we've been talking about it. Highly cratered. What does that mean? It's been hit by a lot of asteroids, comets, all sorts of stuff. What we would call meteors, it's been plastered with them. Why? There's no atmosphere to burn them up. That's why a meteor is a meteorite when it's falling. It's a falling star, a shooting star. It's not really a star. But what it is, we have a big, thick atmosphere. When it falls through it, there's enough friction there, it burns up. Unless it hits the ground, then it becomes a meteor. Okay? Did I say that right? Yeah. No, it's a meteor when it's up there. If it hits the ground, it becomes a meteorite. Yeah, I believe that's right. Well, we'll see later. Okay. But nothing, no atmosphere to slow down or stop those things from hitting, so they all hit the Mars surface. And guess what? They all are aiming for the sun anyway, and Mercury's so close, Mercury gets plastered. Highly cratered surface because it has no atmosphere. Now, our moon also has no atmosphere, almost the same size as Mercury, and it's also highly cratered. Now, it may not be as cratered because it's not. It's further out than Mercury is, so not as many things. Okay. So, okay. Back to the table. I just took that. That's to do that. Now, atmosphere. Oh, I skipped density. Sorry about that. Notice the densities here. What is the densest planet? Say again?
Mercury.
Go a little further. Earth is the densest planet. I told you we were dense, okay? Yes, we are the densest planet, and next to us is Mercury. Notice the first four. What are they called? Terrestrial, because they're rocky, high density. And Emmanuel decided to join us today. Good deal. Glad to have you. Okay. How's your mom? Okay, good. Okay. Maybe I shouldn't have asked, but I was not expecting you. Glad you could make it. How are we doing on time, by the way? You know, it is that witching hour, isn't it? Okay? Let me finish the table, and then you just got in by the skin of your teeth to get crowned present here. Okay? Notice the first four terrestrial planets, the least dense of them being Mars, about 4. This is grams per cubic centimeter. Earth being 5.5. Mercury almost that. Venus still 5. But look at the gas giants. Nowhere close to 5 or 4 or 3 or even 2. They are 1.3, 0.69, 1.3, 1.6. It's a little close to 2. And the one I want you to focus on there, the 0.69. Does anyone know what that kind of a density means? What has a density of 1? Water. So that means if you had a big enough pool of water, Saturn would float. It's that low density. It's mostly gas, okay? The others are too. The gas giants are mostly gas, but sometimes they're pretty dense gases, okay? And they have a cores in there, and I'm sure that Saturn has a core, but on average it would float. 0.69, almost 0.7 density. Atmosphere, Mercury 9, and this I find interesting. Mercury 9, that's a reason we'll talk about that later. Venus and Mars on either side of Earth, mostly carbon dioxide. We wouldn't be able to live there, right? Earth, nitrogen and oxygen. Okay? And then anything beyond, as we mentioned earlier in a slide, hydrogen, helium, and sun methane. Okay? The gas giants, mostly gas. So the gas giants, very low density because they're gaseous, okay? And so forth. The solar energy received, I'll let you, that's just, if you're closer to the sun, you receive more. Farther from the sun, you receive less, okay? That's pretty obvious. All right, we'll end there, and we'll begin with Mercury next time, okay? What's that? Okay. But remind me, before I get carried away next time, that we have already talked about the table. I think I'll remember it, but just in case I don't, remind me. Okay. Do y'all need a little break, or you want to move on to lab time? And I'm beginning to hate that we're in this room now because I need a board to write on. Well, what I'll do, I'll write on the screen. Not going to be pretty, but it'll be doable. Okay. Now that it is lab time, I do need to mark, which I forgot to do last time, but hopefully I got you all. Did any of you leave before 3 o'clock last time? Those of you that were here. I don't recall that you did, but if you did, you slipped out and I didn't see it. I need to mark every day, y'all remind me, at 3 o'clock I have to count roll again. Because the system we use, if you have a lab, you have to mark a lab. Okay, Brendan's still here. Brianna is still here. I just am trying to get names and faces together. Dalen is still here. I thought that was you. Okay, Darius is still here, right there. All right. Orty Elston King was on the roll, but is no longer, so I assume he or she is gone. I guess it's a he. Emmanuel just by his skinny teeth came in. Tara, I see, right here. Okay. Coco in the back. Okay. Bianca came in right there, I remember. James, I remember. Josh, still here. Carrie, still here. Carl, still here. Okay. Someone named Stevens. Is there anyone named Stevens? Okay, still haven't seen whoever that is. Shelby's still here, right? Yeah, I see you. Okay. Brittany hasn't made it in yet, has she? And Terry Wright, got it. We have a Brittany Terry and a Terry Wright, so y'all are trying to confuse me. I have a class this morning, had a class with 3 Joneses in it, and the first initial of all 3 of them was A. Alexis, Elena, and Ashley or something. Y'all are just trying to confuse me. Okay. You didn't need to hear that, did you? Okay, I'm going to close this down because we won't need that anymore. And, here they are. Okay. They were here somewhere. Now, as I said at the very beginning, when we're talking about how we're going to do the course, the first several labs we're going to do as a group. Okay? What is this? 3 students? Yeah. You're not this class. Okay. Which were? Okay. Now, I turned on the light because there's some reading to be done, but I'm going to have to turn it out if I'm going to be drawing on the board. So let's get what it is. Celestial coordinates. We talked about this last time, early in the chapter. I'll let you read most of this, but let's get the general concept down, and I used this before. Let me get my bearings here. I think I'm pretty close to it here. I think pretty close I'm facing north. I don't have a compass in here, but if any of you have good sense of direction, I think that's pretty much north. Okay? Is that right? Anyone want to argue with that? You may be right. I don't know. Let's just say that's north from where I'm standing here. Now, if you drew a line from due north directly over my head, and we're going to name that in a minute, to due south, that would be my local meridian. Okay? A meridian cut. I wish I had my globes down here. In fact, I think I'll run get it. Y'all hang tight. I'm going to pause the sound for just a minute, and I'll be right back because I like using the globe. Forgot to do that. Sorry. So all that I just said about some of those words, they didn't get recorded. Sorry about that, people not here. You should be here. Okay. Let's talk then about some of the shapes here. And this is the description I'm going to make of it over and over again throughout most of the rest of the lab and some future labs. Okay? It's this illustration that we have at the bottom of page 360. Okay? And my drawings are pretty lousy, so don't laugh loud. Okay? Lee. Okay? All right, I think I've got my... So this is going to represent the Earth. Okay? Not a very good representation of the Earth. Okay? And the Earth axis is tilted. Okay, remember I said about 23.5 degrees. So this would be the North Pole right here. Okay, now around the Earth, then our equator is here. Okay, there's the equator. South Pole would be down here somewhere. We happen to live in, what was I going to say, we're residing right now in Bessemer, Alabama, and they don't actually give it a value because they didn't know where we were going to be, but this is going to be our latitude. How far, how many degrees above the equator Bessemer is before you reach it. I'll tell you now, it's about 33 degrees, blah, 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 blah. Okay? So I've drawn that to represent maybe something like 33 degrees. Okay? And there we stand in Bessemer, Alabama. There we are. Okay? Now here's the celestial sphere. Okay? That bowl that's over us. Okay? The point directly overhead, and I said we were going to get to this in a minute, we're there now, this is called our zenith. The point, wherever we are, directly overhead, that's our zenith. There it is, the zenith. This is our northern horizon, and this is the southern horizon. Okay? When I look to the north, that's as far as I can see. I can't see anything below that horizon. Look to the south, I can't see anything below that. Okay? So I've just got the bowl that's on top of it. Okay? Zenith being directly overhead. Now, on that, if I were to project up this way, that same alpha, oh, I'm sorry. Got that wrong. Sorry about that. Not yet. Okay. Okay. That same alpha here, this alpha that was here, this is the alpha there. That's our latitude. Okay? Just to give you an idea of what we're talking about. Here's the equator at 0 degrees. Go north 15 degrees, and you're right there. Go 30 degrees, and you're right there. Pretty close to Mobile, it looks like. I'm in the dark here, I can't tell. And then we're about 3 more degrees north of there. Okay? Approximately. So that's what we mean, our latitude, alpha. Okay? Well, then this would be, if that's our zenith, 33 degrees or so below that, alpha below that, this is the celestial equator. Because this is the equator down here, there's a celestial equator. Okay? Now, from this celestial equator, okay? Now, remember, what is it that makes an equator? Why do we give it that term? Equator? Equal distance from what? North and south poles. So if it's equal distance from the north and south poles are 180 degrees from each other, right? They're straight across from each other. So equal distance between them is 90 degrees. Okay? So if you draw a line 90 degrees from this one, oops, that's not very good. Something maybe about like that. That looks like that's close to 90, probably not exactly. That would then be the North Star, or Polaris. Okay, the North Star right there. Okay, now that doesn't look like 90 degrees. Move it down here a little ways. Yeah, definitely needs to come down a little bit. Let me see if I can make that a little bit better. I told you my drawings stink. Whoa, it didn't take. Okay, let me move this down. The old Tegrity, I could have just done this a lot easier. Okay. Probably not going to do much better here, but let me try it. Does that look more like 90? I think so, maybe. Closer anyway. So here's the North Star, or Polaris. Okay? Because it's 90 degrees from there. Now, what they tell us to do here, I've tried to draw this as best I can here, using what they have. prove that this angle theta here, which is our latitude above the equator here, which is our zenith from the celestial equator there, the angle measurement there, that alpha, is in fact the same as the North Star is from the horizon. Can you show that's true? Huh. Any of you see that? Oh, I was going to point with that. Okay. Okay. I've almost given it away because you see this is 90 degrees here, right? And obviously the zenith is 90 degrees from my horizon, right? So if I take and move alpha that way, I have just dropped alpha that way as well, right? So this has to be alpha here too. Now I was in the U.S. Navy, okay? And one of the things we did in the Navy, now I wasn't the navigator, but we all had to sort of know how to do this. We did what we call celestial navigation. And we would pick out stars at night. At certain times we had to use books and all sorts of things to figure where we were and stuff like this, and plot the stars, and where the stars crisscrossed, that was our location. And back in the old days, that was even before I was young, you know, that was the only way. When they were out at sea and the whole horizon was always the ocean, nothing to break it up, how did you know where you were? Okay? You used the sun and the stars to do. And one star you always tried to shoot was the North Star because that gave you your latitude. You knew exactly which line. If you shot the North Star with a sextant, you knew exactly what latitude line you were on. Then you shoot other stars and you cross those in different ways, and that's how you determine your location. And literally, we did that. Nowadays, they have, just like we do, satellite navigation, GPS, okay? But guess what, folks? If it ever did come to a next war, and you wanted to neutralize our Navy, all you have to do is knock out the computers, knock out the satellites. But guess what? I hope those navigators are still going out there at night and shooting the stars. Can't knock them out, okay? So that's how we determine, and I hope they still do it. Once we went to the satellite navigation, they started cutting back on that kind of stuff, but I heard fairly recently, now with all the threats of cyber attacks, that would be a real good one, okay, to knock us out. I don't think we're doing that anymore. I think we have overcome. So you've just done number one. If you got that down and write your reasoning down, you've got that done. Okay. What's that? That was number one on page 360. We just did it. Prove that the angle alpha, that's the observer's latitude, that's what it was down here, that's what it was here, is the same as the angle alpha of the north celestial pole over the northern horizon. Okay? Say again? Okay. If you want another way to do that, okay, what would you say this angle would have to be? This angle right over here. If this is alpha and this is 90, what would this angle be? 90 minus alpha, right? Okay, you can call that 90 minus alpha. Okay? Now, this is 90, right? Celestial equator to the north celestial pole. Okay? That's 90. And that's alpha. So this angle right here would be 90 minus alpha. Okay? This one, angle here is 90 degrees, right? This one is 90 minus alpha, we just determined, right? So this one would have to be alpha. 90 minus alpha would be this one, so this would have to be alpha. So there's another way to prove it with the angles. Okay, does everybody see it? You'll need to write something down to indicate to me you see how that came about. Okay, we just did the first lab. First question on the lab. What's that? That was on. What's that? And that would be fine with me. Well, I mean, it's already drawn for you, right there. Yeah. If you write in those angles what I just said, yeah, I think that would be fine. Okay? Everybody see, we just did number 1. All right. Flip the page over to page 361. If the celestial pole is at an angle alpha above the northern horizon, that's what we just determined, right? Then we can establish the location of the celestial equator. Where is it going to be? If the North Pole, or North Star, or North Polaris is 90 degrees, is alpha degrees above the northern horizon, where is the celestial equator? It's 90 degrees from it, okay? Or alpha from our zenith, okay? Because if you put this up alpha, you do that up alpha. So that's how we get the celestial equator. I drew that one first because I thought it would be easier to see, but they're doing it sort of the other way. Okay? So from figure 47.1, which is on that previous page, I think that's just still doing the same thing we just did. Okay? Okay, let's go to number 2. What if the celestial pole makes an angle of 40 degrees above the northern horizon? So now we're not calling this alpha anymore. Let's call this 40 degrees. Now the way I've drawn it, that's not 40 degrees. I should move it up some. In fact, I will if you want me to. I heard you arguing and griping and complaining about it, so I'll do that. Okay. I can read your mind. Sort of sick literature, though, by the way. Okay. Let's make it 40 degrees. Something like that. Does that look like about 40? Okay. So if that's 40 degrees above the northern horizon, what is the angle? Oh, and if we do that, that would have to drop the celestial equator down some. So let me do that as well. Okay. Okay. So that would be celestial equator now. Okay. What angle above the southern horizon would the celestial equator be? Say again? I can't hear. A little louder. No, it's 40 here. Remember, this one is 40. That one's 40. So this would have to be 50 because it's 90 minus alpha. You got it. 50 degrees. You've just done number 2. Following? Okay, good deal. Okay, let's go to Quito, Ecuador. Okay, you want to go to Quito, Ecuador? Anyone know where Quito, Ecuador is? You know where Ecuador is? Okay. Boy, y'all need some geography lessons, don't you? Ecuador is in South America. Okay? Here we have Venezuela. Here we have Colombia. Going down the Pacific Ocean here. Here we have Ecuador. E-C-U-A-D-O-R. Guess where that's Spanish for what? Equator! You got it! It sits right on Ecuador, the country Ecuador straddles the equator. And Quito, Ecuador, which happens to be the capital of Ecuador, is almost sitting right on the equator. Okay? So there we are at Quito, Ecuador. Okay? Suppose you are at Quito, Ecuador. Latitude 0 degrees. Where would the celestial equator be? So if you were at Quito, Ecuador, you would have to take this ball and twist it till the equator is right there. Where would the celestial equator be? It would be going right through your zenith, right overhead. The celestial equator would not be at some angle like we had it before. It would be from left to right, east to west, directly overhead. That's your equator. Because you're standing on the equator, the celestial equator would be projected onto the celestial sphere. Right? Okay. So, you got number 3. All right. Now, all of you have the labs, so you can see the next figure, figure 47.2. I'm not going to draw it then, since you have it right there in front of you, but I will point out some things in it. Maybe this will be helpful. Get the light here. Okay, they turned the globe a little bit. They had it pointing this way, now they got it pointing this way. If you have north pointing this way, south celestial pole pointing down that way, you see your globe in the middle, there's your equator, north pole, south pole, the north celestial pole directly above that, and south celestial pole directly above that, the celestial equator there. And this is the Earth in space, basically like this, okay? That's sort of the representation of it. Celestial sphere above here, north celestial pole there, south celestial pole below the horizon, celestial equator going around like this, wherever that is. Okay? Now, really a immediate sun. Okay? You look pretty bright. Can you be our sun? Yes, why don't you be the sun? Okay? All right. Now, no, you're fine, right? You know, you're the sun. That's why I pictured you in the middle of the room. Okay, so here we are. Now, what time of year do you think we are right now? She's the sun now. She's bright, remember? What time of year do you think we are? Okay, this would have been winter. Then the North Pole is pointing away from the sun. So when we get over here, that would be winter. Okay? Because you see, we're way up here, the sun's not shining on us too bright, real low in the sky. Okay. So that's winter. Summer would be when we were over here. I'm getting way away from my microphone because now the North Pole is pointing to the sun. Okay? And depending on which way we're turning, let's say we go this way. If that was summer, this would be fall. Okay. Now, where is the sun relative to the equator? The sun is right on the equator now. In fact, everywhere on the globe, as we spin from the sun, you see the whole planet, don't you? Okay. So on that day, you have equal day, equal night. Or if we were German, we'd say equinox, which we now call equinox. Equal day, equal night, that's equinox. And in the fall, spring, we went through winter, and now it came to spring. Again, we have equinox. Okay? So, we call that position back there the summer solstice, because the sun stands still. It gets the highest point it does. Every day leading up to June the 21st, the sun rises until it quits. It stands still. After that, it starts coming down. Sol, sun, east, still. Solstice. Summer solstice, highest point in the sky. Winter solstice, lowest point in the sky. It drops every day. Every day the sun doesn't get quite as high, not quite as high, until December 21st or so. It stands still, and the next day starts going up again. Winter solstice. Okay? So that's how we get our seasons, because of this angle that the Earth has here. 23.5 degrees. We think they call it an inclination. Okay. So that's what this is showing us. When the ecliptic, the path of the sun, touches our equator, we're at the vernal equinox. When it's on the other side, it's the autumnal equinox. When it's at the lowest point, the sun is below our celestial equator, then we're at winter solstice. When it's the highest point above the celestial equator, that's the summer solstice. Now, I don't know if you know this. I hope this doesn't almost sound sacrilegious, but it's probably pretty close to true. The pagans used to really celebrate winter solstice. The reason was they were always afraid the sun would just keep going down and never come back up again. But when it stopped and started coming up again, they celebrated because they're going to have another year. And when is that? December 21st or so. I'm afraid that's probably the reason we chose December 25th to be our Christmas. They were already celebrating this, so let's just say that's Christmas and have them think they're celebrating that or something. I don't know, because I really don't think the shepherds were out there in the middle of winter, you know. I think they were in warm, you know, thing. But who knows? I'm sorry, I didn't say that. Let's not go there. Okay. So just to get an idea of what's going on here, let's get the time of year when the sun's at the highest. I'm back there now, at the highest. It rises now in the east. Okay, if that's north, there's east, right? It rises actually south of, north, south of, you think? Yeah, it rises north of east. I've got to get turned on. Yeah, because on the solstice, on the equinox, it rises due east. Okay? Second? Yeah, okay. The sun rises on the solstice, on the equinox, with fall or vernal or autumnal. It rises directly in the east and sets directly in the west. Now, when the sun is higher in the sky, it actually rises north of east and then goes up, stays above where it would be in the equinox, and then sets north of west. So it makes a bigger arc and stays up longer. And in the winter, it's the opposite of that. It rises south of and stays south and sets south. Okay? Now, I know that for a fact because our house faces due south, pretty close to due south. And I'm driving my wife crazy because in the morning I get up and open all the blinds, and at night I close them all to keep, either getting hot or cold, whatever it is outside. And on the north side of the house, after spring, I actually have sunlight coming in that bathroom window when I open the blinds down. It's a guest bath, you don't yell at me much for that. Okay. But I couldn't do it if we had a blind in my master bath. Okay. So anyway, that's what this is showing. In the summer season, the moon sun actually rises north of east, goes up higher in the sky, because the sun, okay. Because we're here where we live, the sun never gets directly overhead, not even in summer. It just doesn't get there. Okay, we'll talk about that a little bit later. But it gets higher and higher and higher. So it's always south. Okay, if we did this, like this is our winter, it's lower here, it's higher. So it never quite gets to directly overhead, but it rises further to the east, and that's what these are showing. There's really no question here. Just trying to get the catch. Now, we're going to look next, and the whole reason we're doing this is celestial coordinates. We need to identify where things are, okay? We'll now use the points and circles we've discussed so far to establish, and I guess I need to do this one a little bit more, okay? All right. The two things that we use to identify an object, just like we use latitude and longitude to identify where we are on the globe, to identify where we are on the celestial sphere, for this we're going to use your declination, and we're going to use your right ascension. Okay? Now, those are the two coordinates. This is on page 363. Declination and right ascension. The declination is how far above the celestial equator you happen to be. That's your declination. The right ascension is where you are right or left of the vernal equinox, the spring equinox. Okay? Now, there are some things here that seem to be a little, somewhat strange, but they're true. Points on the celestial equator have a declination of 0 because they're right on the celestial equator. The North Pole would be plus 90, the South Pole would be minus 90 because they're exactly 90 degrees from the celestial equator. Now, here is a peculiar aspect of right ascension coordinate. It's not measured in degrees. No, it's measured in hours, minutes, and seconds. Now, we call them hours, minutes, and seconds. And there's a reason for it. So instead of 360 degrees all around the celestial equator, the right ascension, and that's what we call it, right ascension, is 24 hours around the celestial equator. So basically, we're that 360 degrees, we're dividing into 24 hours. Which, by the way, is exactly how we get our time zones, right? Because when the sun is somewhere over us, it's somewhere else over somebody else. So it's a different time of day. And all the way around the globe is 24 hours, right? So let's do the math. Okay? Now I wish I could, in fact, I may just write on top of this. Okay? Now, we're talking about two different things here. Degrees of arc. How many degrees around the 360 degrees around the celestial equator? And how many hours around the celestial equator? 24. So the question is, this is question number 4, how many degrees of arc are equivalent to 1 hour of right ascension? How many degrees of arc are equivalent to 1 hour of right ascension? Now, y'all just told me a minute ago that you have 360 degrees of arc is the same as how many? 24 hours of right ascension. Basically, that is your ratio. Okay? Now, if you want 1 hour of right ascension, we must divide this by 24 to make that 1. And we would have to divide this by 24, which would make that, say again? 15. 15 degrees of arc is equivalent to 1 hour of right ascension. Divide 360 by 24 and you get 15. That's number 4. Do the math. Okay? Number 5. Okay? Now, hours of right ascension are broken down into minutes of right ascension. How many minutes you reckon are in an hour of right ascension? 60, just like we do time. Okay? So the question here is how many, minutes of right ascension are equivalent to, I need a symbol for that, equivalent to 1 degree of arc. Okay? Well, we just got here that 15 degrees of arc is equivalent to 1 hour of right ascension, right? And what do we say 1 hour of right ascension is? How many minutes? 60 minutes of right ascension. Now the question is, how many minutes of right ascension are equivalent to 1 degree of arc? So how are we going to get this to be 1 degree of arc? Divide by 15, and that will give you 1 degree of arc. Well, if you divide this by 15, what do you get? 4 minutes of right ascension. Do you see that? 4 minutes of right ascension. 1 degree of arc is equivalent to 4 minutes of right ascension. That's question number 5. Do you see it? Understand it? Okay. Now, do you know how we break down a degree? What's the smaller unit from a degree? Minutes. Okay? When you're dividing so many degrees, you divide it into minutes. And guess how many minutes are in a degree? 60. The good old Sumerians, do it again. Somehow they got involved with everything here. They had a base 6 or 60 system, okay? So, you've just told me, whether you realize it or not, that 1 degree of arc was equivalent to, that one up there, 1 degree of arc is equivalent to 60 minutes of arc. So you have to keep up with what you're talking about here. And that 1 degree of arc was equivalent to 1 minute of right ascension. Okay? Well, the question was, how many minutes of arc, so we're looking for this, are equivalent to 1 minute of right ascension. I'm sorry, this was 4 minutes of right ascension down here, not 1. 4 minutes of right ascension. So how are we going to do that one? I'm sorry? What's the question again? No. Okay. This doesn't indicate, but I sure hope it's true. I think this is that your class is a second mini-term class. Go to this. It doesn't say on here, but it should somewhere on here, but it doesn't. Oh, wait, no, I'm sorry. No, it doesn't. This indicates it is now. Yuck, folks, I blew it. When I looked today, they said this was a second mini-term. What you ought to do is go to the registrar's office and see if indeed this class did make. It may be that it only made for second mini-term. So why don't you go to, you know where registrar's office is? You're a little early. So go there and see if the first mini-term class made. When I talked with them today and they told me this room was open until second mini-term. So either they told me wrong or your class may have been canceled. So check with them. So that says it does start today. Sorry. We may have to move, folks. I don't know where we'll move to, but we may have to move. I know there's some classrooms open, so what we may do from now on, if indeed they do have a mini-term class coming in here, which they told me they didn't, but if they do, what we'll do at lab every time, whether it's at 3 or at 2:30, whenever that is, we'll just move to a different room on this level. But at 12:30, this is the only thing available. But by the time we get to 2:30 or 3, there'll be other things available. Does anyone know if there's anyone else waiting for orientation out there? You don't see anyone, do you? That guy was early, but he's not that early. I would think people would be piling up. Okay, so what we had here was 1 minute of arc, which is 1 degree of arc, which is 60 minutes of arc, was equal to 4 minutes of right ascension. The question is, how many minutes of arc is equivalent to 1 minute of right ascension? How would we get that? You have 4 down here. Divide by 4. Divide this by 4, and that gives you 1 minute right ascension. And if you divide this by 4, that gives you 60 divided by 4. 15 minutes of arc. So, there's your last question, number 6. How many minutes of arc are equivalent to 1 minute of right ascension? Just got it there. 15. Everybody see it? All right. Flip a page. All right. We don't have a celestial globe. Wish we did. We don't. Okay? What I have here, when we first started going to a planetarium, I went to the one at Birmingham Southern. I thought it might be easier for students to get to because it was just right up the expressway from here. Okay? I don't know if y'all were around several years ago. Birmingham Southern went through a really bad period of financial difficulties. So at first I heard they were either shutting down the planetarium or going to start charging for the planetarium. And since I didn't have a budget to support doing that, I called Stanford. And when I did, they said, yep, ours is free. So we started going there and have gone there ever since. I still don't know what's going on with Birmingham Southern. They have a nice little planetarium, but actually a lot of things are a little bit easier at Stanford, and it's not that far from here either. Anyway, okay? So what we're going to do is figure out, as if we had a celestial globe, and by the way, where I was coming from there, the lady who was there at Birmingham Southern gave me some star charts, okay? And that's what we're going to use. I let students use them the first couple of years, and gradually all of them left except the one I did. I couldn't keep hold of them. They kept walking away. So what I'm going to do, I'm going to use what we've just been talking about and determine what stars we have. What they're giving us is right ascension. Now, if you look back in your notes or on the lab sheet here, what is right ascension measured from? Say again? Yeah, degrees from what? Look at page 363, that figure at the top of the page. Where is right ascension measured from? Say again? You see that figure at the top of the page, figure 14.5? Okay, so where the celestial equator crosses the ecliptic, and when does the is there a is this an orientation class? Did it make 4 o'clock? Okay. They told me in the registrar's office that it start in the second. Okay. Are all these students here for orientation? I know one was. He went to check. y'all here for orientation? You are for orientation. You do. Okay, then. What we'll do is we'll move across them all. Okay, thanks. All right, from now on, folks, at lab time, what we'll do is stop and move across the hall. So, somewhere across the hall. So I'm going. Now, what we're doing on your lab sheet on page 364, you see it gives you some locations. Like we were talking about, these are your kind of like latitude and longitude. Actually, longitude and latitude. Okay. So what we're doing, remember, where is right ascension measured from? From the second. Where is right ascension measured from? What? Yes, where the celestial equator crosses the ecliptic. Well, that happens twice a year. Which one are we going to measure from? No, those are when they're highest points. Solstice, sunset, still, equinox, equal day, equal night. Spring or autumn, we're going to use spring. When about the spring equinox? March. March 21st, approximately. Okay, so what we're going to use, we don't have a celestial globe, so what we're going to use is the star chart here. And I'll illustrate it on the first one. So the first one, we're starting from where the, okay, I don't know if y'all can see the star chart from here. You see there's a circle here. You see that circle there? It's exact, this is the North Pole right here. North Celestial Pole. So that circle that's equidistant from the North Celestial Pole is the equator, celestial equator. Very good. Now there's a dotted line here that sometimes north of the North Celestial Pole, sometimes hits the celestial equator, sometimes hits it, and sometimes it's below it. What do you reckon that dotted line is? The ecliptic. Very good. So it crosses it. You can see right where it crosses. There's a dotted line crossing that one. And let's get it lined up. And by the way, there's a string hole that you line up here with that up here. And then we see, where are we? Here's February, March, April. There is a vernal equinox. It starts at that point. And if you look at it, by the way, that is right on March 21st. Okay? So that's where we begin. Okay? And it says we do right ascension 6 hours and 43 minutes. Okay? Right ascension 6 hours and 43 minutes. Well, 6 hours, 1, 2, 3, 4, 5, 6. That would be 7. 43 would be something about almost 3/4 of the way there. Okay? Somewhere right in there. Unfortunately, I can't see the date. I know it's sometime, this is June, there's July. It's sometime after the 30th of June, 1st of July. Let's just call it, let's say it the 4th of July. I can't see for sure, but let's estimate that. So I'm going to scoot around here until I have the 4th of July. Nice date anyway. And by the way, this has been used and abused so much. There we go. 4th of July. There's the 30th of June, and there's approximately the 4th of July. Understand we may have a little slot there. Okay? So that gives me the right ascension. Okay? Now we do declination. What is declination measured from? What? It's like your latitude, but what it's measured from. Latitude is measured from the global equator. This is measured from the celestial equator. So the celestial equator is this circle here, and it says minus, meaning south of the celestial equator, not toward the North Pole, away from it, about 16 degrees. Okay, now let me give you a little background here. This chart is designed for a latitude of 40 degrees north, okay? So if that's 40 degrees north, this is 90 degrees here between the equator and the North Star. So this would be, if this is designed for 40, this would be 50 degrees down here, right? Just like we did before. The southern horizon is 50 degrees south of the celestial equator, right? Just like we did before. So 50 degrees minus 16, let's just call it minus 16 and a half. That's not quite halfway down, right? Okay, 25 degrees would be halfway down. So let's go just a little. Oh, there's a really bright star there. Can anyone see it?
No.
Sirius! Are you serious? Yeah, no, this is Sirius. It's Sirius. Does anyone remember from the chapter? Anything special about Sirius? The brightest star in the sky. If you can see it, the brightest star in the sky. Okay? Now, that's relative magnitude. All right, I just showed you how to do this. Y'all wrote down Sirius, right? Who's going to be first to try it on your own? All right, brave soul. Okay? Where does he start? Right ascension. And right ascension is measured from where? The what? Where the equator crosses the ecliptic. At which time of year? Spring. So that's going to be right around March the 21st. Have you found it? Yeah. So there's where the ecliptic crosses the equator. So line up your string there, and you should be right around March, February, March. Yeah, you're looking pretty good. And then where do you go from there? 6 hours and 22 minutes. Okay? So count this way. 1, 2, 3, 4, 5, 6 hours and 22 minutes. 20 minutes is about a third of an hour, so that's right about there. What date do you see there? Looks like June the 27th, he said. Okay? Spend June 27th around there until that's under your string. So he got his 6 hours, 22 minutes right ascension. Now, he really lucked up, didn't he? How do you do declination? Celestial equator, exactly. But this is how far from the celestial equator?
Minus
52 degrees, 40 minutes. Since this is based on 40 degrees north, how far is our southern horizon?
50.
Minus 50. We can't see it! The star is beyond what we can see, but it's some star south of, let's see what the bottom thing you can see here, some star south of they'll show it there, of Columba, the constellation Columba, Columba, a star south of Columba. That's all we can say because we can't see below the horizon. Okay? Columba. Columba. I don't know that constellation at all. All right. Goodness gracious, you living right, aren't you? Okay. 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 Who wants to try it next?
I'll do it.
You want to try it next? Okay. Where do you begin?
Okay, well, I begin at summer,
Spring equinox, which is about
March.
March 21st, approximately. It's where the celestial. What happens at spring equinox?
The sun and the moon are
Close. Celestial equator crosses
the
ecliptic. Exactly. And you see the ecliptic is this dotted line here, and there's one, but that's in September, so that will be. Yeah. Can you move this? One? Okay. Can I set it right there?
Sure.
Okay.
Okay, so this is March.
Okay. This is what you line up with down here on this string. all the worse for wear.
Yeah, it's kind of sticking a little bit.
Yeah, it is. It's been ripped and torn. Okay. So yeah, you're real close. There's March Lane, so you need to scoot a little bit further that way. So here's the hole that you line up. Okay. So right. I can't get it to turn now. There it goes.
Sorry.
No problem. February, March, there. Somewhere right in there, 21st. There it is. See, the ecliptic is crossing the equator.
Okay.
Okay?
So
Where do we go from there?
it's 18 hours and 35 minutes.
And you count around this way. So start counting. This is 1, 2, 3,
4, 5,
6,
7, 8, 9, 10, 11, 12,
Who else would be there, right?
13, 14, 15, 16, 17,
18. And then it says, how many minutes? 35. Just about 18 and a half. So that would be somewhere there, maybe
about here.
the 30th of, what month is that? November, January. 30th of December?
Yeah, but
Okay, so let's do the 30th of December. Still, it's down here. I'm not there yet. There we are. Somewhere pretty close. Okay.
and so then I need my plus 38.
844. So that's more than about a third of the way up from the celestial equator toward the North Pole. A little over that. Oh, there looks like a bright star. What is that?
Vega.
Vega. V-E-G-A. Vega. Thank you. Good deal. Vega. Number 3. Who wants to do the next one? Brave souls here. Come on. Oh, don't be shy. Okay, here we go. And where do we begin? Yeah, vernal equinox. So you'll need March 31st here. That's where the celestial equator, that's the solid line that crosses the dotted line. That's it right there. So look right under you. Yeah, March 31st. Right there under. That looks like it, and how you check it is you have to hold both ends of the screen, line it up there, and the screen holds down there. And sure enough, you're right at where you put it across the equator. And where do you go from there? To the right, and that's this way. Looks like it's about 5 hours. Go down, hold still, and then do 1, 2, 3, 4, 5 hours and 12 minutes. It's going to be somewhere in there. So that's somewhere before June. Let's say June 10th. It's not quite that far. Swirl June 10th around till that gets. Around June 10th. Wind up. And then you do minus 8 degrees 15 minutes. That's not very far below the equator. So you've got a bright star fairly close below the equator. Rigel or Regal. R-I-G-E-L. R-I-G-E-L. Really bright star. Good deal. Who's next?
I'll do it.
All right, good deal. Where do you start?
March 21st.
March 21st. Okay. Yeah, and how you check it is the celestial equator. That's the solid line crosses the ecliptic with the dotted line. You're right on it. And where do you go from there?
Right, 7 hours.
7 hours and a little over 7.5 hours. So you start counting. Here, okay, that would be 6 here. 1, 2, 3, 7.5. Be somewhere under there. Let's say July 15th or so. So spin July 15th down until it's under your stream. Okay, and we may not have done exactly right. Just a little bit above the celestial equator. You see a bright star there? Just above it. No, not that far. Just a few degrees above. Procyon. 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 I don't know these stars, by the way, folks, so don't feel bad. Procyon. Procyon. Who's next? Come on, don't be shy. All right, good deal. Where do you begin? March 21st, which is vernal equinox. What's true about March 21st, vernal equinox? Yeah, the equator crosses this ecliptic, and there you have it. See, there's the ecliptic, there's the equator, the top right there. Yeah, you don't know.
Thank you.
You cross exactly there. And where do we go from there? Yeah, a little over 14.5 hours. Yes, I know. 14.5. Oh, you lucked out. Where's that? October 29th. Let's spin October 29th under your stream. Okay, she's over there, and where do you go from there? And there's a minus, so that's south of the equator, but guess what? We're 60 degrees, 38 minutes south of the equator from 40 degrees north. Below the horizon, because our horizon's at 50 degrees south. So guess what? You lucked out too. It's something south of the constellation Centaurus. Centaurus. Something south of Centaurus.
Can you spell that again?
Centaurus. I thought you would recognize that name. A centaur?
Yeah. I don't know how to spell it.
Okay. That was the man's torso in a horse's body, or something like that. This is the, what's that? I don't know. I just made it up. No, I thought a centaur was, isn't that? Yeah, that was the
bullhead, man, buddy.
Yeah, that's it. Oh, okay. Got it. I thought it was horse. Okay. So there we did our stars. Actually, easier, you lucky people, you, are the constellations. Because guess what? You just have to get approximately close to get a constellation. So who wants to go first on the constellation? Don't be shy. Okay, he heard it was easy, so he raised his hand finally. Okay. I got you figured. Okay. Where do you begin? Should have a clue. Where do we begin everything? Okay. Yeah, well, it's where the celestial equator that crosses the ecliptic, but that happens twice a year. Yeah, March. You're in September, so you're on the vernal. I mean, you're on the optimal. You gotta get around to the vernal. Okay, get in place there. Okay, bring down. Yeah, you got something. Sure. Enough the ecliptic crosses the equator there. And where do you go from there? Right ascension. Okay, the other way. That feels like when you go the other way. Yeah, the 11 right there. Oh boy, you can September 4th. So spin September 4th around until it's under your string. Okay. Now, where do we go with declination? And that means 50 degrees north or south of the equator. Okay, 50 degrees north would be over halfway, so what constellation is just past halfway up there? Little, she was an actress, Ursula Major. No, that was somebody else. Okay. Ursa Major. Anyone remember who Ursa Major is?
Big Bear.
Big Bear, you got it. Ursa meaning bear, major meaning big, I guess. Okay. Next. All right.
How do you spell it?
Oh, U-R-S-A, Ursa Major, M-A-J-O-R. Ursa Major. Okay. Boy, she's spinning right away here. Okay. Starts with the. Yep. And you see that's pretty close to where the eclipse crosses the equator. Okay. Oh wait, I know what's wrong. This is over the hole. A little bit further. Okay. Okay, and then you go.
The string or the wheel?
No, you count off hours. Right ascension. How many hours? Okay, yeah, you would think it goes right, but you go left. All right. That's 11, but that he did that. There it is, and right, and you don't see a thing. So something. What would that be? Near the 1st of January, kind of. Okay, try that. Spin around till you get 1st of January under your string. Okay? And then minus 25 degrees. Now, remember this is set up for 40. So this would be minus 50 down here. So halfway in there, what looks like you're there? Yeah, I can't remember. Okay, halfway, I don't know if it's that. I would say let's go with that. That's my first. Okay, yeah. Okay. Sagittarius. I think it is. I don't know if that's my birth or not. It's one of the, what do you call those? Zodiac.
Zodiac.
Let's call it Sagittarius. It may be Scutum, I don't know. It looks like it's probably Sagittarius. Okay. S-A-G-I-T-T-A-R-I-U-S. Sagittarius. S-A-G-I-T-T-A-R-I-U-S. Okay? Who's next? All right, good deal. The third constellation. She's spinning it around so she can start at vernal equinox, which is where the celestial equator crosses the ecliptic. And sure enough, there you're right on it. Good deal. Okay, May 8th. Very good day. And then you do 20 degrees north. Now remember, this is 90 degrees from the equator to here, so 20 is going to be pretty far up. I think that may be the very first constellation you see there. Oh, that's too far north. What's this one here? Which one is it? Oh. 45. waiting, don't I? Huh? You got to go through the motions anyway. What do you do first? Where do we begin?
March 21st.
March 21st. Okay? You line up the string there, you have to notice that the celestial equator and the ecliptic cross right there, that's where you start. And where do you go? 1 hour, so you go there. And boy, it's hard to say. I would say that's probably near April 1st, maybe. And maybe a little past April 1st. Okay, let's try that. And then plus 60. No, he was probably the other way. Plus 60 is a little over halfway. Because 45 would be there. I think it's right there. You see that one? Funny looking word. Cassiopeia, or Cassiopeia. I'll spell it for you. Okay? Cassiopeia. Cassiopeia. Now remember the story of that one because I've heard it just about every time. Sort of makes a little W or something looking. Actually, that's supposed to be a chair. And the reason is some princess or queen or somebody displeased somebody, I can't remember what the story was, and got chained to a chair. And then, if I'm not mistaken, Perseus, the brave warrior, is on his way to try to rescue her. Okay? They made up all sorts of stories. I don't know how they got these pictures out of those stars in the sky. But I guess they had a lot of time to imagine them. Okay? Who's next? Come on, don't be shy. Not everybody's done it yet. I see your hand up, don't I? Yes, you thought you were scratching your head. No, you were raising your hand. Okay, where do you begin? Okay. Keep that around to the bottom. Okay. Okay, right. Okay. Hold it this way, yeah. Yeah, that part going first. Okay. Now when you hold the string over that string hole, you see that your celestial equator, the circle here, crosses the dashed line, which is the ecliptic. You're right on the right place. And where do you go from there? 13 hours, right? That's what you're doing. Right ascension, so count around this way. Hours. No, don't move. No, just count hours. 1, 2. Right there, okay? And what date do you see there? Okay, 7th of September? 7th of October. Spin 7th of October around there to your string. You find the constellation, and where you look? Minus 50, which is right on the southern horizon. So what constellation you see right above the line there? Good old one we talked about before. Centaurus. C-E-N-T-A-U-R-U-S. Centaurus. 13 degrees right ascension, 13 hours right ascension, minus 50 degrees declination. C-E-N-T-A-U-R-U-S. It's like the Taurus Ford car with a C-E-N in front of it. Okay, Centaurus. All right, who's next? Last shot. Who hasn't done it? Do I have to volunteer somebody? Help me. Some of you haven't. Who? Thought you were hiding, didn't you? No. Okay, where do you begin? This way. And we begin at the vernal equinox, which is, now this is the autumnal equinox, so that's in September. You have to scoot around here until you get the equator crossing the ecliptic. The equator is the circle here, the dash circle. Scoot that around until March 21st. Right, somewhere close to there, and how you can tell for sure when you line up the string, your ecliptic should be crossing the equator. Sure enough, it is. See it? Okay. So from there, you count what? 7 hours right ascension. Go to the right 7 hours. You're right there in the middle of nowhere. I can't see it. Let's just say about July 1st. Right, so there's July. Scoot around to July 1st. All you're doing is trying to find a constellation, so hopefully we'll find one there. Find that up with the moon down here. Oh, yeah, there it is. You're right. Okay, and where do we go? Minus 40, meaning 40 degrees south of the equator. So here's the equator. You only have 50 degrees you can see, so 40 would be just above that. I think you're a good old, right there. Canis Major? Yeah, Canis Major. Anyone know what a canis is? Canis? Second? Oh, canine. Okay, your canine teeth, your dog teeth. Canis Major. I can't remember who he was the pet of. But anyway, he was some dog that's up there. Okay, the big dog. There's a little dog somewhere up there too, Canis Minor. But this is Canis Major. And by the way, say again. Oh, C-A-N-U-N-I-S. C-A-N-I-S. Major. M-A-J-O-R. Canis Major. All right, good deal, folks. Now, well, I may not leave that off. All right. Part B, page 365. On the ecliptic, that's our dotted line here, remember? Locate the position of the sun on June 21st. Now, we don't have small pieces of self-stick paper, so let's find June 21st here. I'm not far from it. Okay, June 21st, right there, I think it is. And that, by the way, is the highest point that the sun, the ecliptic, is above the celestial equator. Does anyone want to hazard a guess of how many degrees it is above the celestial equator there? Make a guess. What is the tilt of the Earth? Nope. 23 and a half. Get used to that. You're going to be using it a lot. 23 and a half degrees. So it'll be 23 and a half degrees above the celestial equator. Now the question here, does the sun rise exactly in the east on this day? So how do you tell where the sun is rising then? Well, this is supposed to represent the night sky, and the sun is over here, so you track around the sun, that's on the ecliptic, till you get way over here, and does it rise exactly? Oh no, I'm sorry, I did that wrong. Okay. What we have to do is move the sun. Now, you can't move the sun really, can you? But where is the sun? Okay, I don't know if y'all can see that. The sun is on the ecliptic. Okay? But this is night sky. Right behind the sun are three little stars here. The one furthest to the right on the ecliptic, that's where the sun is on June 21st. So what I'm going to do is rotate those three little stars around, and it's the very farthest one to the right, until it's just coming above the eastern horizon. What time is that? It looks like it's about 4:40. About 4:40. Oh wait, that wasn't the question. It says, does the sun rise exactly in the east that day? No, it rises north of east. And it seems to be rising, let me find it again, there it is. It seems to be rising about, I'm guessing about 20 degrees north of east. I'm just making a guess there. So the answer there is no. It rises north of east. Remember when I said in the summertime the light comes in my northern windows, okay, pretty brightly. Now, it says rotate until the sun sets, okay? Remember the sun is right behind that little star there, that third star over, right there, the group of three. I'm going to try to set that star, which the sun is right in front of it. You can't see the star, but it's on here. So I'm going to scoot, 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 scoot. There, it's just about to set right there. Okay? Set somewhere there. Now, estimate to the nearest 15 minutes the amount of time the sun is above the horizon on June 21st. Remember I said it was about 4:40 over here? That was sunrise. And let's see what time sunset is over here. It looks like about 7:20. 7:20. Okay? No lights came on. There they did. Okay. 7:20. All right. I think I'm going to clear this out of the way. I'll probably regret it, but it's just too crowded right now. Okay? We said the sun came up at 4:40 in the morning, right? It set at 7:20 p.m. Now, this was a.m., and that was p.m. That's a really ugly p, isn't it? Okay, p.m. Okay. Now, I need to find out how many hours it was up. Now, you can count on your fingers or something or another, but if you use military time, that works pretty nicely. What time is 7:20 in the evening on the 24-hour clock? 19:20. Were you in? Oh, okay. 19:20. Good go, though. Subtract that. You get a 0 here. You're going to have to borrow some minutes from this hour. Make the 1918. How many minutes in an hour? 60. So you add 6 to 2 and you get 8. And that would be 40 minutes. 18 minus 4. 14 hours, 40 minutes. So calculate, I'm sorry. Okay? Says estimate to the nearest 15 minutes the amount of time the sun is above the horizon. Something just blinked. Oh, I guess the lamp's coming on. Above the horizon. And it says enter your estimate on table 1. So if you turn over to page 366, table 47.1. Now here's some problems, folks. Whoever did this, in that first table, the first column, they say the SEC of the sun. I don't think they mean the Southeastern Conference. I don't think they mean seconds of the sun. I have a feeling they mean DEC, which would be declination of the sun. And what did we say the declination of the sun was on the 21st of June? Which was the summer solstice, as high as it gets in the sky. 23.5 degrees north, or plus 2330, or plus 23.5. However you want to say it, okay? That's the declination of the sun. How many hours of daylight did we just calculate? 1440. And then if the next question says the number of hours of darkness, we would have to subtract 1440 from 24, except I'm going to have to borrow one, so I'm going to subtract it from 23 hours, 60 minutes. 9 hours, 20 minutes. Perfect. Everybody see that? 9 hours, 20 minutes. Subtracting it from 24, which is the same as 2360. Just makes it easier to subtract. Make sense? All right. Let's now go to December 21st. Someone want to try it? Who hasn't done it yet? I know there's at least one, two. Just 2 people haven't done it yet. Who wants to try? Okay, one of you. All right, he's grinning. He wants it. All right. What you got to do is set up for December 21st, and move December 21st around to this position down here. Number 21st. That's 30. Oh, wait, I'm sorry. Okay, a little bit further. Oh, yeah, you're right. Okay. All right. Now, what we need to do is line this up. I'm sure we all need to get we're pretty close. And where is the sun then? The sun is at the end of that dash there, okay? There's not a star nearby, but at the end of that dash, the dash just above that. So now we might need to spin that around to sunrise. So that end of the dash, keep your eye on the dash. And that dash is just about to rise right there. Let's bring that around here. And let's estimate that to be about 7:20, 7 and 8. 7:20 a.m. is sunrise. So on the margin somewhere there, do 7:20 a.m. Okay? Just like we did before. Now we're going to move the end of that dash, right there, around here till the sun sets. Getting close, right about there, don't you think? End of that dash. And that looks like about, I guess maybe 5:40. No, I'm sorry, 4:20. 4:20. About 4:20 p.m. Okay? So, huh?
Can you repeat that?
4:20 p.m. and what was the first one? 7:20 or 40? We wrote it down. Huh?
Yeah, 7:20.
7:20 and 5. Oh wait.
4:20.
4. Okay. 4:20. 7:20 and 4:20. We'll use them. I don't know. Okay, so let's say it down. The sunrise was at 7:20 in the morning. Is that what you said?
Yes, sir.
And it set at, was it 4 or 5? 4:20 p.m. Okay, let's change that 4:20 to military. 16:20. Okay, this is approximate, folks. What does that give us? About 9 hours of sunlight. And if you had 9 hours of sunlight, subtract that from 24, and you get 15 hours of darkness. Okay, it's approximate. It said in there's 15 minutes. I think we can do that. So that's what goes. Oh, and what was the declination of the sun on December 21st? Where was the sun then? Okay, yeah, I'm sorry. The on page 365 it says repeat this process for December 21st. So we turn to the table, and the declination of the sun then was what? Minus 23:30 or 23 and a half or whatever, 23:30 south, whatever you want to call it. And the number of daylight hours was 9 hours, and the number of darkness hours was 15. Okay, about like we got before, only reversed. Yeah. All right. How about March 21st? Who wants to do it? I think there's only one left, isn't there? God. Okay. Did you done one? Oh, you did. Okay. Has everyone done one then? Is it close? It's not yet. We got a couple minutes.
What's a couple?
Okay.
57.
I don't want to cheat you out of your tuition dollar. I want you to get every penny of it. Okay? Now, what can you tell me about March 21st? Yes, the equator's right on the ecliptic. Right there. That's where we were starting all the others. So if we move that around to sunrise, where the ecliptic crosses the equator, you can see right where that is. Sunrise, get it right at sunrise, and guess when the sun comes up then? 6 in the morning. There's 5, there's 6. And then you scoot that around to when that sun sets. That's where the ecliptic crosses the equator. It's 6 p.m. at night. How many hours of daylight?
12.
How many hours of darkness?
12.
Guess what we call that? Equinox. Equal night, equal day. We knew that without doing it, didn't we? If we'd have thought. Okay? And what was the declination of the sun on that day? 0. The sun, the ecliptic was crossing the equator. It was not a north or south. Very good. All right. I don't think we have time to go to Altegard, Norway, do we?
No.
Okay, we're going to have to start at Altegard, Norway next time. So bring your coats and your scarves and your, okay. We will be in Altegard, Norway. And by the way, let's see, how are we going to do this one? The first, let's see. Yeah. What we're going to do is the first 2 hours at least will be in chapter 5. Okay? Chapter 15. Okay? If we finish chapter 15 before that 2 hours is over with, we'll probably stop right when we finish the chapter and then pick up and finish this lab and start the next lab. Now, if at 2 hours we haven't finished chapter 5, we'll probably continue until we do finish chapter 5. And when we do finish chapter 5, we'll stop then and finish this lab. And then when we've got 30 minutes to go, we'll have our test. Okay? So we'll play it that way. All right? Sorry that we have to break it up this way. Don't have that much more to go, but we have a little bit longer to go. Okay. Good deal, folks. Yeah.
Okay. The reason why I'm late every day is because my class before this one is at 12:15.
Yeah.
And I'm running from Birmingham campus
That's
to
it
here.
here. Don't worry. If I have at least one in every class. Some classes 2 or 3. They either have to leave early or start late. Yeah. No problem.
It's crazy.
I know. But getting schedules to work is crazy. Hey.
So imagine how my time schedule is. I'm going to be tired